Why does the universe make sense? That might sound like a strange question, but think about it. Why does everything follow rules at all? From the way light moves to how stars burn, from the tiniest atoms to the largest galaxies, the universe behaves in regular, repeatable ways. There are patterns, there are constants, there are laws. But why should reality have rules in the first place? Why doesn't it all just act randomly? We take these laws for granted, gravity, motion, energy, as if they've always been there. But where did they come from? Why do they work the way they do? Could they have been different, and are they truly unbreakable? The hidden grammar of reality. In everything we see, from falling leaves to spinning galaxies, there's a sense that things behave in a way that feels orderly, structured, and repeatable. We've come to call these patterns the laws of nature. It's as if the universe is following a hidden script, a grammar that shapes how everything unfolds. In language, grammar tells us how to form sentences, how words should be arranged, and how meaning is passed from one mind to another. We rarely think about grammar when we speak, yet without it, our words would be meaningless noise. In the same way, the universe appears to follow a set of invisible rules that shape every event, from the motion of stars to the firing of neurons in a brain. Why isn't everything just pure chaos? If we imagine a universe where things just happened with no reason, where apples could float up one day and fall down the next, where atoms randomly flew apart, and where time ran forward and backward without warning, then there would be no way to understand or predict anything. It would be a universe with no memory, no meaning, no structure. But what we have instead is a universe where certain actions always lead to certain results. Water freezes at 0 degrees Celsius. Planets orbit stars along predictable paths. One possible explanation is that we live in a kind of selection bias. In a universe without order, nothing complex could ever exist. There would be no stable atoms, no stars, no chemistry, no life. So maybe we find ourselves in an orderly universe simply because it's the only kind of universe where anyone could exist to ask the question. This idea doesn't really explain why the laws are the way they are, but it does hint at why we might expect some kind of structure. Still, that doesn't fully solve the puzzle, because not only is there order, but it's surprisingly beautiful and understandable. The laws of physics can often be written in simple mathematical equations. The same rule that governs a falling rock can also explain how the moon orbits the Earth. The same basic building blocks make up stars, oceans, and our own bodies. It's as if reality is following elegant, interconnected rules that seem carefully arranged. Grammar in language evolves from minds. It comes from humans who learn, change, and pass along ways of communicating. But in the universe, the grammar was already there, long before any minds existed. Who or what wrote these rules? Were they always there? Did they emerge with the universe itself, like a kind of cosmic operating system booting up with the Big Bang? Some physicists and philosophers have suggested that the laws of nature might be more like habits that the universe developed over time, that they weren't fixed at the start, but settled in like grooves in a well-worn path. Others argue that the laws are eternal and unchanging, a kind of cosmic code that exists outside of time, waiting for a universe to follow them. But both ideas raise even more questions. If the laws developed over time, what governed their development? If they were always there, why do they take the form they do and not something else entirely? There's also the strange fact that the universe seems to allow beings like us to understand its grammar. That's not something we had to expect. After all, we're just small creatures on a rocky planet orbiting an average star. Yet somehow, our minds can grasp ideas like gravity, relativity, and quantum mechanics. The grammar of reality is not just consistent, it's comprehensible. It's as if reality speaks a language we're able to learn. This has led some thinkers to propose that the universe is not just orderly, but deeply mathematical. In this view, the grammar of reality is made of math itself, and the universe is a kind of unfolding equation. every object and event is a term in the formula. In practice, math has proven to be the best tool we have for describing nature. Equations predict particles we haven't yet observed. Models drawn from mathematics guide telescopes to distant galaxies. And yet, nobody really knows why math works so well, why numbers dreamed up by humans should so perfectly match the behavior of stars. It's tempting to look for a deeper reason. Maybe the universe is part of a larger pattern we don't yet see. Maybe our physical world is only one version of reality among many, and we live in the one that follows this particular grammar. Or maybe there is no deeper reason. Perhaps the rules we see are just the ones that happen to be written, and there are no others. Are physical laws really laws, or merely patterns we observe? A law sounds final and certain. It tells us what must happen. But when scientists talk about physical laws, they don't mean it in quite the same way. These laws aren't commands. They just take countless observations and wrap them up into a simple formula. That formula is a map of the behavior we've noticed. Take Newton's laws of motion. For centuries, they worked incredibly well. They told us how objects move, how forces act, how momentum changes. But eventually, scientists discovered situations where Newton's rules didn't hold up, especially at very high speeds or on very small scales. That's where Einstein's theory of relativity and the strange world of quantum mechanics came in. This shows us something important. The laws we talk about aren't perfect truths. They're models we build based on what we observe. When our observations grow more detailed, when we find new ways to test and measure, we often need to change the laws. That doesn't mean the universe is changing. It means our understanding of its patterns is changing. Imagine a world where no one is there to watch. No humans, no animals, no conscious minds. Would gravity still exist? Would electrons still spin? Stars still burn? Atoms still bounce? Most of us would probably say yes. It feels natural to believe that the laws of physics are part of the universe itself, not part of our minds. But the truth is, we don't know what laws are like without observers, because we've never seen a universe without anyone in it. When we say that light moves at a constant speed, we're describing what we've measured. When we say that matter can't be created or destroyed, we're describing what we've never seen happen. But in both cases, these are generalizations based on experience. They are patterns that have never failed, yet that doesn't guarantee they never will. A black swan doesn't seem possible until you see one. What if the laws of nature aren't fixed at all? What if they're not eternal truths, but things that emerge from the universe shaped by its own structure and history? Some scientists have proposed that the laws might evolve like species in nature. In the early universe, things may have behaved differently. Over time, certain regularities may have stabilized, while others faded. If this is true, then the laws we see today are just the current state of a changing system. Others have asked whether the idea of law is even the right way to think about it. A law suggests certainty. But the quantum world is full of uncertainty. Particles can be in two places at once. They can appear and disappear randomly. They don't follow rules in the way classical objects do. Instead, we use probabilities to describe what might happen. In this world, cause and effect seem blurry. So if the building blocks of reality are not fully predictable, can we still say there are laws? Even time itself is strange in this context. We experience time as a flow, a one-way arrow that takes us from past to future. But many equations in physics don't care which way time goes. They work the same forwards and backwards. So where does the direction of time come from? It doesn't seem to be built into the basic rules. It seems to arise from something else. Maybe from how energy spreads or how memory works. Once again, the law-like behavior we think we see might only be part of the story. Maybe the universe just is, and what we call laws are just the regularities our minds notice. After all, we're pattern-seeking creatures. Our brains are wired to find order. We see faces in clouds, shapes in stars, rhythm in noise. So when we look at nature and find structure, Are we discovering something deep or projecting something familiar? The only tool we have to study the universe is the human mind. With all its strengths and limits, we collect data, form ideas, test them, revise them. We look for rules because rules help us survive, build, and understand. But the rules we find are always filtered through us. We don't see the universe as it is, we see it as we can. In quantum physics, the act of measuring seems to affect what we measure. Until we observe a particle, its state is uncertain. This has led to strange interpretations, that reality is not fully real until it is observed. If that's true, then the laws we describe may only make sense in a world where observers like us exist. The pattern and the mind that notices the pattern may be linked. That doesn't mean reality is imaginary. It means our version of reality is always shaped by the tools we use to describe it. A microscope shows one kind of truth. A telescope shows another. Equations reveal deep structure, but only the parts we can put into numbers. There may be layers of reality we haven't even begun to notice, patterns too complex, too subtle, or too strange for our current understanding. Still, it's remarkable how much we have uncovered. Even if the laws are not absolute, even if they're just models, they have real power. They let us build bridges, cure diseases, launch satellites, and decode the age of stars. The patterns we describe may not be the whole truth, but they give us a handle on something vast and mysterious. However, every discovery also reminds us how much we still don't know. We map one piece of the puzzle and the rest grows larger. We write one law and another exception appears. We solve one mystery and uncover two more. If the laws are truly out there, we may never see them completely. And if they are something we build in our minds, then we may always be shaping reality as much as discovering it. Constants of nature. Why these numbers and not others? All across the universe, certain numbers show up again and again. They are called physical constants, and they shape how everything in the cosmos behaves. One of them is the speed of light, about 299,792 kilometers per second. Another is the gravitational constant, a tiny number that controls how strongly objects attract each other. Others include Planck's constant, the charge of the electron, the strength of the electromagnetic force, and many more. These values seem to be part of how reality works. If you drop a ball on Earth, or send a probe to Mars, or look at the light from a star millions of light years away, these constants always show the same values. That consistency allows us to do science. It lets us make predictions, build machines, and explore the universe. But why is the speed of light not faster? Why is it not slower? What decides that it moves at just under 300,000 kilometers per second and not at 200,000 or 500,000? There's nothing in the laws of physics that forces it to have that exact value. We just measure it and find that's what it is. But why? If the speed of light were different, the universe would be completely different too. In fact, tiny changes to these constants could make life, or even stars and planets, impossible. If gravity were just a little stronger, stars would burn too quickly and collapse. If it were weaker, stars might never ignite. If the charge on the electron was slightly off, atoms wouldn't form the same way. Molecules might not be stable. Chemistry itself could fall apart. So it's not just that these numbers are interesting. They seem fine-tuned. They sit in a narrow range where things work just right. Perhaps there are many universes, not just one. In this multiverse view, each universe has its own version of the constants. Maybe in some other universe, gravity is 10 times stronger. Maybe light travels at half the speed. Maybe atoms don't form at all. Most of these universes would be dead, empty, or chaotic. But in a few, like ours, everything lines up in just the right way. And of course, it's only in one of those right universes that anyone could exist to notice it. Some versions of modern physics, including string theory and inflation theory, suggest that multiple universes could exist, each with different starting conditions. If that's true, then maybe the constants we see are not special. We just live in one of the few universes where they make sense. Still, Even if there are other universes, we can't see or test them. We only have access to this one. So the mystery remains. Why do these values work here, in this universe? Could they have been different? And if they could have, why weren't they? Some constants are pure numbers, like the fine structure constant, which controls the strength of the electromagnetic force. It's about 1/137th. This number has no units, no connection to any specific measurement. It's just a ratio. It doesn't matter whether we use meters or miles, seconds or years. This number stays the same. Physicists have called it one of the most mysterious numbers in nature. Nobody knows why it has this exact value, and tiny changes to it would tear the universe apart. Many scientists have tried to find deeper patterns that might explain these constants. Maybe there's an equation, still undiscovered, that ties all these numbers together, a kind of master formula that explains everything. This dream is sometimes called the theory of everything, a single set of rules that unites gravity, quantum mechanics, and all the forces of nature. If such a theory exists, maybe it could show why the constants have the values they do, but so far that theory remains out of reach. Other researchers have explored whether the constants might not be constant at all. Could they drift slowly over time? So far, experiments suggest they don't. Light from distant galaxies, billions of years old, behaves just like light from a lab on Earth. Gravity seems to pull the same way everywhere we look, but the search continues. Even a tiny variation, if found, would change our whole picture of reality. In recent years, scientists have started tying units of measurement directly to fundamental constants. For example, the meter is now defined in terms of how far light travels in a certain fraction of a second. The kilogram is tied to Planck's constant. In a way, this locks the constants into the system. We define our measuring sticks by using the values of these constants. That means we no longer measure some of them. We use them to define other things. But this can make it even harder to ask why these constants are what they are. If we've tied our tools to the constants, then the values are always the same by definition. These constants seem to point to something beneath the surface, something we haven't yet uncovered. Whether they are accidents, necessities, or part of some hidden logic remains unknown. But every equation we write, every experiment we build, and every star we study carries their mark. When did the laws of physics begin? It's easy to assume that the laws of nature have always been there. But if the universe had a beginning, then we have to ask whether the laws themselves had a beginning too. Did they come before everything else? Or did they appear with the universe? The earliest moment we can talk about with any confidence is the Big Bang. Before the Big Bang, there was no space to expand into and no time ticking forward. At least, that's what our current understanding says. But if there was no time, then there was no before in the way we normally think about it. That makes it very difficult to ask what existed earlier, including whether the laws of physics already existed, waiting for the universe to arrive. Some physicists think the laws of nature were born along with the universe. That when space, time, matter, and energy came into being, the rules they follow also came into being. In this view, the laws are not timeless, eternal things. They are part of the universe, just like galaxies and atoms are. They came packaged together with the first moment, like software booting up when a computer turns on. The universe turned on, and the rules came with it. But other scientists and philosophers believed that the laws had to exist first, that they were already out there, in some sense, before the universe began. Maybe they didn't exist in space and time, but in a kind of abstract realm, like mathematics. In this view, the laws are more like a blueprint. The universe is what happens when those rules get applied. It's like a game that begins when someone presses start. But the rules of the game were already written. If the laws came after the universe began, then what decided how the universe would behave in that first moment? Why did it unfold in this particular way and not some other way? Why did particles form? Why did space expand? Something must have given the universe its direction. But if there were no laws yet, How could anything behave in any predictable way at all? On the other hand, if the laws were already in place before the universe existed, then where were they? What does it even mean to say something exists outside space and time? Can a law exist without anything to apply it to? It's hard to picture. Maybe it's not right to talk about when the laws began. Because time, the very idea of before and after, may itself be part of the laws. If time is something that was created along with the universe, then trying to ask what happened before time existed might be like asking what's north of the North Pole. Some models in theoretical physics suggest that space and time may not be fundamental. They may be made out of something else, something more basic. In that case, the laws of physics might not be built on top of space and time. They might be part of the machinery that creates space and time. If true, then the laws didn't start at a time. They make time. There are also ideas that suggest the universe didn't begin with a bang, but with a bounce, a collapse and re-expansion of a previous universe. In this picture, the laws might survive from one cycle to the next. Maybe they were there in the universe before ours. Or maybe the laws themselves change slightly each time the cycle resets, like a universe slowly learning new behaviors across cosmic ages. What would guide the evolution of laws? Would there be some meta-law, a law about how laws change? And if that meta-law exists, when did it begin? We find ourselves pushed back again and again to the same edge, the moment of origin. What started everything and what guided it? We also can't ignore the role of causality. Cause and effect seem to form the backbone of science. One thing leads to another. Energy moves. Motion spreads. But causality needs time. You can't have a cause before there is a before. So if time begins with the universe, then maybe causality does too. That would mean there is no cause for the universe. It just is. A spontaneous event without a before, governed not by earlier events, but by the rules that define the event itself. Quantum mechanics gives us a strange glimpse of how something might arise from nothing. In the quantum world, particles can appear and vanish, borrowing energy from nothing so long as they give it back quickly. Some have suggested that the whole universe could be like this, a kind of quantum fluctuation popping into existence because it was allowed to. But even a random event needs a framework. So again, we come back to the laws. Some thinkers, especially in philosophy, suggest that the laws of physics might be like logical truths, like how 2 + 2 must equal 4, no matter what. In that view, the laws couldn't be different. They exist the way logic exists. That's a powerful idea. But it doesn't give us much detail about how or why the physical world follows these logical patterns, or why there is a physical world at all. There's also the possibility that what we call laws are not the real bedrock. Maybe they are just the patterns we see from our limited view, the way waves look smooth from far away, even though they're made of countless moving water molecules. The deeper level might not look like laws at all. It might be more like a wild, shifting landscape, and what we call laws are just the average behavior of that landscape over time. What we do know is that the universe we see has rhythm, symmetry, and balance. It doesn't act like pure chaos. Something holds it together, shapes its path, defines its options. But whether those rules are eternal, or created, or evolving, whether they existed before time, or are born from time itself, is a question that may go far beyond science as we know it. Why is there a speed limit in the universe? At the beginning of the 20th century, Einstein showed that space and time are not separate things, but part of a larger structure called space-time. And within this space-time, the speed of light is a boundary that can't be crossed. Why shouldn't something just go a little faster, with enough energy? Why is light the limit and not sound or gravity or some other force? What's so special about that exact number? To understand this, we have to look at how motion and energy are connected in our universe. When something moves faster, it gains more energy. That's easy to see when you throw a ball. The faster you throw it, the harder it hits. But in Einstein's view, as something moves closer to the speed of light, its energy doesn't just rise steadily, it starts rising sharply. It takes more and more energy to go just a little bit faster. And as you get closer to light speed, the energy needed grows toward infinity. That means you would need infinite energy to move any object with mass at the speed of light. Not a lot of energy, not just more than we can build, but truly infinite. And since infinite energy is impossible, that speed becomes unreachable. Light, which has no mass, travels at that speed because it doesn't need any energy to do so. But anything with mass, even something as small as a proton, can only get close, never quite reach it. This limit doesn't just apply to physical objects, it also applies to information. You can't send a signal faster than light. You can't communicate instantly across space. No matter how advanced a technology is, no matter how clever the method, the speed of light remains the upper boundary. This is why we can't talk to astronauts in real time when they're far away. Even light from the sun takes over 8 minutes to reach Earth. Light from the nearest stars takes years. And light from the most distant galaxies takes billions of years to arrive. Which is why we see them as they were in the distant past. The speed of light is connected to deep properties of space and time. It appears in the equations of electromagnetism, the rules that describe how electric and magnetic fields behave. In those equations, light is a wave that travels through empty space, and its speed comes out naturally from the values of electric and magnetic constants. But even then, we're just describing how it behaves, not why those constants have the values they do. In other words, we can say the speed of light is determined by certain physical constants. But that just pushes the question back. Why are those constants the way they are? Some scientists believe that the speed of light, like other physical constants, could have been different. If the strength of the electric force or magnetic force were different, maybe light would move slower or faster. Others think the speed of light might be fixed for a deeper reason. Maybe it's built into the logic of the universe itself. Maybe it's not just a property of light, but a property of space-time. In Einstein's equations, the speed of light isn't just the speed of a wave. It's the fastest that cause and effect can work. It's the speed limit of causality. If you could go faster than light, you could send messages into the past. You could change the order of events. Cause could follow effect. Time would become broken and inconsistent. Physics would lose its grip. The entire structure of the universe, all the rules of how things move and change, would fall apart. That's why the speed of light is a kind of boundary in the structure of reality. It divides the possible from the impossible. Inside that limit, space and time behave in predictable ways. Outside it, nothing works. Another way to look at it is through light cones. In relativity, every event in the universe has a light cone, a shape that shows where light from that event can reach over time. Anything inside the cone can be affected by the event. Anything outside the cone can't. These cones fill the universe and overlap in a way that keeps cause and effect moving forward. If the speed of light were infinite, there would be no cones. Everything could affect everything instantly. There would be no structure to time, no separation between events, no way to build a story of what happens and when. In a sense, the speed limit sets the pace at which things can change, spread, and interact. Without it, the cosmos might be chaotic or completely frozen. The fact that there is a limit and that it's not too fast or too slow is part of why we're here at all. It gives the universe a kind of natural delay that holds everything together. Symmetries and the roots of natural order. In physics, symmetry means that a system behaves the same way even after you change your point of view. Imagine spinning a perfect circle. No matter how much you turn it, it still looks the same. That's symmetry in space. Or imagine watching a clock tick backward. If the laws of physics stayed the same even when time reversed, that would be symmetry in time. It turns out that symmetries like these are deeply connected to the laws that govern the universe. The connection is so strong that many scientists believe symmetry is the foundation of all physical law, the reason why the rules exist in the first place. Instead of laws causing symmetry, maybe symmetry is what creates the laws. This idea came to light in a big way during the early 20th century, when a German mathematician named Emmy Noether showed that for every symmetry in nature, there's a matching conservation law. If the laws of physics don't change over time, then energy is conserved. If they don't change from place to place, momentum is conserved. If they don't change when you rotate something, angular momentum is conserved. This means that the deep patterns we see in nature, the things that stay the same no matter how we move, turn, or wait, are the reason certain quantities never disappear. Energy doesn't vanish because time itself has a symmetry. Momentum doesn't vanish because space is uniform. These are signs that the universe runs on hidden balances. It's almost like the universe has a kind of fairness built into it. You can't get something for nothing. You can't create or destroy energy at will. You can only move it, change its form, or pass it from one place to another. This balance comes not from any outside force, but from the quiet strength of symmetry. Symmetry is everywhere in physics. Electric and magnetic fields are part of the same system because of a kind of rotational symmetry in space and time. Light itself is described by equations that remain unchanged under certain shifts in perspective. The reason electrons behave the same way in different atoms, or why the strong force always binds quarks together in the same way, comes down to underlying symmetries in the structure of matter. Even the particles that make up everything, electrons, quarks, photons, neutrinos, are classified by their symmetries. These particles come from fields that fill all of space, and those fields behave in certain ways because of their built-in symmetries. Change the symmetry, and you get a different set of particles, with different masses and different forces. This is why modern physicists use symmetry like a kind of guidebook. If they want to understand a new force or predict a new particle, they look for the kind of symmetry that might allow it. This method has worked again and again. The discovery of the W and Z bosons, the gluon, and even the Higgs particle were all guided by symmetry arguments. In a way, symmetry tells scientists what's allowed and what's not, which doors are open and which ones are locked. But symmetry is not always perfect. In fact, some of the most interesting parts of the universe come from when symmetry breaks. Think of a pencil balanced upright on its tip. In theory, it could fall in any direction, left, right, forward, or back. The situation has perfect symmetry, but when it actually falls, it chooses one direction, and that symmetry is broken. The rules haven't changed, but the outcome no longer looks balanced. This kind of symmetry breaking happens in nature all the time. It's believed to have happened in the early universe just moments after the Big Bang. At the start, all forces may have been united, part of one symmetrical system. But as the universe cooled, the symmetries broke and the forces split apart. Gravity, electromagnetism, and the strong and weak nuclear forces may have all come from the same origin, separated only by these hidden fractures in symmetry. Even mass itself might be a product of broken symmetry. The Higgs field, which gives particles mass, is thought to work because of a kind of symmetry that broke in the early universe. Without that breaking, all particles might be massless, flying through space at the speed of light. There would be no atoms, no stars, and no life. So symmetry not only creates order, it also creates diversity. It allows simple rules to give rise to complex outcomes. A perfectly symmetrical system might look clean and elegant, but it doesn't allow for much variety. Breaking the symmetry introduces structure, shapes, patterns, and differences that give the universe its texture. Some scientists even think that our entire universe could be the result of a broken symmetry. If the laws of physics can change based on how a symmetry is broken, then maybe different parts of the universe, or different universes entirely, have different outcomes. The version we live in may be just one of many possibilities, chosen by the way symmetry broke in our part of reality. This takes symmetry from a tool of physics to something more like a creative engine. It doesn't just explain why things stay the same, it explains how things become different. The more we understand about symmetry, the more we realize it may be at the root of both order and change. Another surprising connection is between symmetry and time. In everyday experience, time seems to flow one way, from past to future. We remember the past, not the future. Stars burn fuel but don't unburn it. But the laws of physics, especially on small scales, don't have a built-in direction. They work the same forward or backward in time. That's a kind of symmetry too, called time reversal symmetry. So where does the arrow of time come from, if the laws don't require it? One answer may lie in the universe's overall structure, and in the growth of entropy, a measure of disorder. As entropy increases, time appears to move forward. But the laws themselves still hold that symmetry. It's as if time's arrow is not in the rules, but in the way the universe unfolded. These insights show how deeply symmetry shapes everything we see. It allows complexity to rise from simplicity. It even helps explain why anything at all can happen the way it does. And yet, for all its power, symmetry still leaves questions. Why does our universe have the symmetries it does, and not others? Are they unique, or could they be part of a wider system, where different regions obey different rules? Is there a deeper symmetry still hidden beneath the ones we know? One that explains not just the particles and forces, but the very reason for the laws themselves. These questions continue to drive the search for a unified theory, a set of ideas that brings all forces and particles under one great symmetrical structure. The dream is that one day we'll find a final symmetry, one so perfect and deep that all of physics flows from it naturally. Until then, we explore the universe like puzzle solvers, looking for repeating patterns, balancing shapes, and the quiet signs that somewhere behind it all there is a structure. Could the laws have been different? String theory tries to explain all the particles and forces in nature using tiny vibrating strings of energy. But to work properly, string theory needs extra dimensions, not just the 3 of space and 1 of time that we're used to, but as many as 10 or 11 in total. These extra dimensions can be curled up or shaped in different ways, and depending on how they are arranged, the laws of physics that emerge can change. It's like building a machine with different parts. Depending on how you set it up, you get different behavior. In this case, you get different universes. Physicists call this collection of possible setups the string landscape. It's a space of possibilities, perhaps containing trillions upon trillions of different potential universes, each with its own version of reality. In some, stars might live for only a few seconds. In others, space might be frozen. Some might not allow matter to clump. Some might not allow time to exist at all in any way we understand. If that's true, then the laws of physics we know are just one option in a huge menu. Another idea that leads to the possibility of alternative laws comes from inflation. The theory that early in its history, the universe expanded incredibly fast in a brief burst. According to some versions of this theory, inflation didn't just happen once. Instead, it keeps happening in different places, creating many bubble universes within a much larger multiverse. Each bubble could cool down in a different way, leading to different physical laws inside. Again, our universe would be just one of these bubbles. So what would a universe with different laws actually look like? If you raise the strength of gravity, stars might collapse too quickly. If you lower it, they might never form. Change the charge of the electron, and atoms fall apart. Alter the masses of quarks, the particles that make up protons and neutrons, and nuclear reactions inside stars stop working. Change the balance of the 4 fundamental forces, and you might end up with a completely different structure. Not all changes lead to chaos. Some adjustments might still allow complex systems, just ones that don't look like what we see here. Maybe there could be other kinds of chemistry. Maybe there are forms of matter we've never imagined. Maybe even other kinds of life, built on different rules. These ideas are difficult to test, but computer simulations have helped scientists explore what might happen if certain constants were slightly different. In many cases, the results are dramatic. Galaxies never form, stars explode too quickly, or atoms don't bind. But in other cases, things still work, just differently. These models suggest that the laws we have may not be the only possible set that leads to complexity. There might be a small range, or even a wide one, where something interesting can happen. Still, even if other laws are possible in theory, we don't know if they actually exist in reality. The other universes, if they're out there, are far beyond our reach. They may be hidden behind cosmic horizons, beyond the limits of light and time. Or they may be completely separate, existing in other dimensions or other branches of reality that we'll never touch. If there are other universes with different laws, can we ever hope to find evidence for them? Can we use math, theory, or experiment to peek beyond the boundaries of our own reality? Or will we forever be limited to the single example we happen to live in, a sample size of one, trying to guess the shape of the whole? Somewhere out there, in the silent corners beyond our reach, the rules might follow a completely different script. Nether's theorem and the deep link between symmetry and law. In 1915, during a time of great scientific change, a quiet revolution happened in mathematics and physics. It came from Emmy Noether, a brilliant German mathematician who solved a deep mystery that had puzzled the greatest minds of the time. What she found was a fundamental truth about how the universe works, a hidden bridge between symmetry and law called Noether's theorem. Let's say you do an experiment today, and then do the same one tomorrow. If nothing in the laws of physics has changed between now and then, if the rules are the same at both moments, then the system is said to have time symmetry or time invariance. Noether proved that whenever time symmetry exists, energy must be conserved, not just sometimes, always. If the universe plays fair with time, it must also play fair with energy. The same is true for space. Imagine sliding an experiment to the left or right, or moving it from one room to another. If the results are always the same no matter where you place it, if the laws don't depend on where you are, then the system has spatial symmetry. Noether showed that this symmetry leads directly to the conservation of momentum. And if you rotate the system, say spin it 90 degrees, and nothing changes in how the physics behaves, then the system has rotational symmetry. That leads to conservation of angular momentum. That's why spinning planets keep spinning, why figure skaters spin faster when they pull in their arms, and why satellites orbit smoothly around Earth. What Noether did was uncover a blueprint that links every kind of symmetry to a specific kind of conservation. For every continuous symmetry in a system, there's a quantity that must stay the same as time moves forward. And this connection works both ways. If you see that something is always conserved, like charge or energy, you can trace it back to a symmetry that lies beneath the surface. This might sound abstract, but it's actually a key part of how physicists understand reality. They don't have to guess what's conserved. They can look at what symmetries a theory has, and those symmetries will tell them which physical quantities will remain constant. In fact, some physicists think the symmetries are more real than the quantities themselves. That energy conservation, for example, is just a reflection of the deeper truth, that the universe treats all moments in time equally. This kind of thinking has had a huge impact. When physicists built the standard model of particle physics, they didn't just plug in numbers or guess how particles behave. They used symmetry principles as the foundation. And from that foundation, the particles and forces almost fall out on their own. Quarks, gluons, photons, and the weak force all arise naturally once you set the right symmetries in place. Even the strange and delicate Higgs field was predicted because of how it fits into the larger symmetry structure. When scientists turned on the Large Hadron Collider to look for the Higgs boson, they were following Noether's logic, pushed forward through decades of theory. But Noether's theorem does more than help with particle physics. It also plays a role in the wider study of the universe. In general relativity, the symmetry of space and time itself is built into the fabric of space-time. The equations that describe how matter curves space are deeply tied to the symmetries of those equations. Noether's theorem helps explain why energy conservation becomes more complicated in curved space-time. Because in some cases, time symmetry is broken by the very shape of space. In quantum mechanics, Noether's ideas show up in the structure of quantum fields. These fields have built-in symmetries, and those symmetries define which particles exist and how they interact. If a field has a certain symmetry, it will lead to a conserved quantity, like electric charge. That's why electrons always have the same charge. Even in the evolution of the early universe, Noether's theorem offers insight. During the Big Bang, the universe may have started with very high symmetry, a kind of perfect balance in all directions, with all forces unified. But as the universe cooled, these symmetries began to break. And yet, even as symmetry broke, Noether's rules still held. One of the most striking examples is baryon number, the count of heavy particles like protons and neutrons. It seems to be conserved in our universe. That symmetry, if it truly exists, explains why matter doesn't just vanish or turn into something else without warning. But if that symmetry were to break in subtle ways, it might explain why there's more matter than antimatter in the universe today, a mystery that still puzzles scientists. Noether's work is also a rare example of something that connects very different parts of physics under one umbrella. From the orbit of a moon to the decay of a subatomic particle, the same rule quietly runs beneath everything. Even now, over a century after her discovery, physicists are still uncovering new consequences of her theorem. In advanced fields like string theory and quantum gravity, symmetries take on more abstract forms. Some are hidden or gauge symmetries, where the system changes in invisible ways that still lead to real consequences. Others may be broken at high energies, only revealing their effects at the tiniest scales. And in all of this, Noether's logic still applies. If there's a symmetry, there's a conserved quantity. If a quantity is conserved, it must come from a symmetry. That simple two-way path lets physicists build bridges across the most complicated landscapes in science. What breaks a law of physics and what doesn't? Sometimes we hear people say that a law of physics has been broken. Maybe it's in the news or a headline online or even a new experiment that gives a strange result. But what does that really mean? Can a law of physics actually be broken, like a rule in a game or a traffic law? Or is there something deeper going on? Something that just looks like a break but really isn't? To start, it's important to understand that when scientists say something breaks a law of physics, they usually mean one of two very different things. The first is a genuine mystery, an observation that doesn't match what we expect based on everything we know. The second is just an illusion, something that seems to go against the rules, but really doesn't when you look closely. Let's take the second case first. Imagine someone drops a ball and it suddenly floats upward. That would seem to break the law of gravity. But if you learn that the ball is filled with helium and the person is underwater, then it all makes sense. It's not breaking gravity. It's obeying a more complete set of rules: gravity, buoyancy, and the way gases behave in fluids. This happens a lot in science. A rule might look broken when we only understand part of the system. Maybe a machine generates more energy than it uses. A violation of energy conservation? Not usually. If we track every piece of input, chemical, thermal, even small electric currents, the extra energy can be explained. It's not a miracle. It's a misunderstanding of what's really going on. These illusions of law-breaking disappear once we include all the relevant factors. But sometimes, experiments push into areas where our current laws don't quite work. These are the real puzzles. Not just misunderstandings, but signs that we might be missing something fundamental. And when that happens, scientists don't throw out the laws immediately. They test, they repeat. They try to rule out every possible error, because the laws we have now have survived countless tests. And if something seems to break one, it might mean the law needs to expand, not vanish. For example, Newton's laws of motion worked perfectly for centuries, but when scientists began measuring things moving at very high speeds or inside strong gravitational fields, the old rules started to fall short. Einstein's theories of relativity didn't break Newton's laws. They included them as special cases. At low speeds and weak gravity, Einstein's equations give the same answers as Newton's. But when you get to the edges, near light speed or near a black hole, you need the full theory. A broken law can mean that we're seeing the edge of where that law works, and a new, broader law is waiting to be discovered. Another example comes from quantum mechanics. Before it came along, people believed particles moved in smooth paths, like tiny planets. But in the quantum world, particles don't have precise positions and speeds at the same time. This doesn't break classical physics. It replaces it in a new domain. Classical physics still works for big things like cars or baseballs. But at atomic scales, the rules are different. Again, nothing is broken. The laws simply change when you zoom in far enough. Sometimes, though, the idea of breaking a law gets more dramatic. Think of conservation laws, things like conservation of energy or momentum. These are considered some of the deepest rules in physics, and yet there are moments when scientists see something that looks like a violation. One famous case involved a type of radioactive decay called beta decay. In early experiments, it looked like energy wasn't conserved. A neutron would decay into a proton and an electron, but the energy and momentum didn't quite add up. At first, it seemed like the law of conservation had failed. But instead of giving up on it, physicist Wolfgang Pauli made a bold guess. Maybe there was another particle being released, one that carried away the missing energy and momentum. This particle had to be tiny, neutral, and very hard to detect. That particle, later named the neutrino, was eventually found. The conservation law held. The mystery just revealed something new and hidden in the process. This is a common pattern in physics. An apparent break in the rules leads to a new. That's how dark matter was first proposed. Galaxies were spinning too fast. According to the known laws of gravity, they should have flown apart. Something seemed wrong, but instead of throwing out gravity, scientists suggested an unseen form of matter, something that adds mass but doesn't give off light. The search for dark matter is still ongoing, and we don't yet know the full answer. But the idea of a broken law has again pushed us to expand our understanding. There's also another kind of law breaking that's more subtle, when a law holds in most cases, but not in all. We see it in the early universe, where forces that were once unified began to behave differently. The symmetry that once existed became broken, and new rules appeared. A perfect system can break its own symmetry and create structure. That's how magnets form, how crystals grow, and how the universe evolved from a smooth sea of energy into galaxies, stars, and planets. So, what would actual law-breaking look like? Something that can't be explained, even with more complete knowledge. Something that repeats in experiments, yet defies all known logic, and can't be folded into any broader theory. That kind of event would truly shake physics to its core. It hasn't happened yet. Every time a law seemed to fail, it turned out the problem wasn't the law. It was our understanding of the full picture. But scientists are always on the lookout. They design experiments to stress the laws, to test them in extreme conditions. Particle colliders look for rare events that might hint at something new. Astrophysicists watch the skies for strange signals, bursts of energy, odd gravitational patterns, unexplained alignments, all in the hope of catching a real crack in the framework. The laws of physics aren't commandments from above. They're models we've built, step by step, to match what we see. And like any model, they can improve. They can grow more detailed, more accurate, more powerful. A real break in the laws wouldn't mean the universe is chaotic. It would mean we've reached the limit of what we currently understand. And that's often where the next great leap begins. This is why scientists remain cautious. They don't claim a law is broken based on one strange result. They test, retest, and compare results across the world. That's what happened with faster-than-light neutrinos in 2011. A headline-grabbing event where particles seem to move faster than light, breaking one of the most sacred laws of physics. But after careful checking, the anomaly was traced to a loose cable and a faulty GPS connection. It wasn't the law that was broken, it was the equipment. Still, That moment showed the openness of science to being wrong. If the results had held up under scrutiny, physicists would have rewritten the rules. It wouldn't have been the end of physics. It would have been the start of a new chapter. The laws of physics are both fragile and incredibly strong. They depend on evidence, not belief. They remain in place only as long as every test agrees with them. But that's exactly why they've lasted. Emergence. Are some laws just collective illusions? The idea of emergence changes how we think about what a law of physics really is. Instead of being a rule written into the foundation of reality, an emergent law is more like a pattern, something that appears only when many parts interact in certain ways. It's a bit like how a traffic jam forms on a highway. No single car causes it. The drivers aren't trying to create it. But when enough vehicles behave a certain way, the jam appears. In the world of physics, temperature is one of the best examples. If you look at one single particle, a lone atom, it doesn't have a temperature, it just moves. But if you gather billions of atoms together, all bouncing around, you can define a temperature based on how fast they move on average. Temperature isn't a property of any one particle. It's something that only exists because there are many particles. It's emergent. The same is true of pressure. One atom hitting a wall doesn't create pressure, but a swarm of them, all bouncing off the wall again and again, does. Pressure is the average effect of millions or trillions of tiny impacts. Again, it's not a basic feature of matter. It's a pattern that shows up when lots of matter is involved. So are the laws that describe these patterns truly laws of nature? Or are they more like useful shortcuts, summaries of how huge numbers of particles tend to behave? Take the second law of thermodynamics. It says that in any closed system, the total entropy always increases. But at the microscopic level, the basic laws of motion don't care about time. Yet when we zoom out to look at big systems, a box of gas, a cooling planet, a dying star, entropy always seems to rise. Time only moves forward. Why? The answer may be that this arrow of time is an emergent feature. The individual atoms don't have a preferred direction, but their combined behavior leads to one. It's like how individual birds in a flock don't know they're making a swirling shape in the sky. Each one just follows a simple set of rules. Stay close, don't crash, match direction. The pattern, the swooping motion, emerges on its own. You could erase one bird or even 100 and the flock would still form. It's the same with entropy. The overall rule seems solid, but it comes from the crowd, not the individual. If emergent laws come from many parts acting together, could different sets of parts lead to completely different rules? Could there be other kinds of universes where different types of emergence happen, where the laws are different, not because the basics are different, but because the crowd behaves another way? Some physicists think this might be true. The laws we observe, like thermodynamics or fluid dynamics, may not be baked into the fabric of space and time. Instead, they might just be the result of the specific ingredients our universe happens to contain. Swap out the building blocks, and the patterns might change. For most of physics history, gravity was seen as a fundamental force. Newton described it as a pull between masses. Einstein showed it as the bending of space-time. But in recent years, some scientists have suggested a bold idea. What if gravity itself is emergent? One version of this idea comes from the study of entanglement in quantum mechanics. When two particles are entangled, they're linked in a way that doesn't seem to depend on distance. Changes to one instantly affect the other. This strange connection has led some researchers to propose that the shape of space-time, and even the pull of gravity, might emerge from patterns of entanglement across vast numbers of particles. In this view, gravity is a byproduct of quantum information flowing through the universe. Gravity may not be fundamental in the way we once thought. Instead, it might be a large-scale illusion, something that only appears when we zoom out far enough. This also helps explain why some rules break down when we zoom in. At the level of atoms, friction disappears. Gases stop behaving like smooth clouds and start looking like tiny particles bouncing around. Thermodynamics gets fuzzy. Time becomes harder to define. The rules that work so well for large systems begin to lose their grip because they were never meant for the small scale in the first place. They weren't written for atoms, they were written for crowds. But water is really made of individual molecules. The smooth surface of a lake is an illusion created by trillions of tiny pieces. The laws that describe how waves move or how water boils are emergent. Even consciousness might be an emergent phenomenon. A single neuron doesn't think or feel. But when billions of them connect in complex ways, a mind emerges, thoughts arise, emotions appear. This is still one of science's great mysteries, how something like awareness can come from matter. But the pattern fits. Emergence may explain not just how the world works, but how we experience it. There are risks in pushing this idea too far. Not every pattern is a law. Some are coincidences, some are just statistical noise, and some apparent laws only hold under certain conditions. But the power of emergence is real. It explains why systems as different as hurricanes, brains, flocks of birds and stars all show order without anyone planning it. The order grows out of interactions. Emergent laws may be the bridge between the chaos of the microscopic world and the structure of the world we see. They allow simple things, like atoms and photons, to form complex systems with rules that seem as strong as steel. But under that strength is something fragile, a dependence on scale, on number, on interaction. Many of the truths we see around us, from the way heat spreads, to the way planets orbit, to the way we think and feel, aren't fixed at the base of the universe. They are patterns that rise up from the hum of countless tiny parts, each playing its simple role. The thermodynamic arrow. Why do laws favor forward time? Where does the arrow of time come from, if not from the deepest rules of the universe? The steady rise in entropy is one of the few rules in physics that shows a clear direction. That's why many scientists think the arrow of time comes from thermodynamics. The universe leans towards messiness, towards spreading out, toward randomness. And that, many believe, is what gives time its direction. This view of time as an effect of entropy is called the thermodynamic arrow of time. It's not a law on its own, but rather a consequence of how countless particles behave when left alone. They don't gather themselves into neat shapes or reverse their paths. And so, time moves forward, from low entropy to high. But why was entropy low in the past? If the second law says entropy increases, it must have started low. Otherwise, there would be nowhere for it to rise from. So why did the universe begin in such an ordered state? Why wasn't everything random and chaotic from the start? The early universe, just after the Big Bang, was incredibly hot and dense. But it was also extremely smooth and uniform. There were tiny ripples, yes, but overall, it was low in gravitational entropy. That smoothness is what allowed stars, galaxies, and life to eventually form. It gave the universe the room it needed for entropy to grow. Some scientists think that inflation stretched the universe into this smooth state. Others wonder if there's something deeper about the beginning of time itself that created this special condition, but no one knows for sure. All we know is that this low entropy beginning is what makes the thermodynamic arrow possible. It also explains why we remember the past, but not the future. Memory is a physical process. It involves storing information, organizing matter in a way that reflects something that happened. But storing anything means using energy and increasing entropy somewhere else. It's a one-way action. We remember past events because entropy was lower then, and our brains could record that information. We don't remember the future because entropy hasn't increased in that direction yet. The same goes for cause and effect. A match lights a candle, a button opens a door. These sequences make sense to us because they follow the flow of entropy. Lighting the match releases energy, spreads heat, and raises entropy. You can't undo it. The process leaves behind traces, heat, ash, light, that show it happened. There's something strange, though, about how tightly this arrow is linked to human experience. Time feels like it's always flowing, always moving forward. But at the microscopic level, that motion doesn't exist. The particles in your hand don't feel the passage of time. They just move according to basic rules. They have no preference. This makes some physicists wonder whether the arrow of time is an illusion, or at least a local feature. Could there be places in the universe where entropy is decreasing, where time flows in the opposite direction? Or is the arrow something that only exists because of the special conditions in our region of the universe? There are theories that explore this. One idea says that time might be symmetrical on the largest scale, that the Big Bang was the middle, not the beginning. On either side of it, entropy increases and time flows outward in both directions. In one direction, that's our universe. In the other, it would be a mirror image, with time flowing away from the Big Bang just as it does for us, but in the opposite sense. If that's true, then before the Big Bang might not be a time we can access, but a kind of reverse universe, governed by the same rules, but unfolding backwards. These are speculative ideas, but they show how strange the arrow of time really is. Even black holes obey the arrow of time. When matter falls in, the event horizon grows and entropy increases. This has led to the idea that black holes have the highest possible entropy of any object. They're like cosmic sinks for information, where disorder reaches a maximum. And even when black holes evaporate through Hawking radiation, slowly losing mass, the process still follows the arrow. The radiation spreads out. The universe cools. Entropy climbs. Quantum indeterminacy. Quantum mechanics has been tested again and again and found to be incredibly accurate. It powers technologies like lasers, GPS, semiconductors, and quantum computers. But even now, it still feels mysterious. Because instead of telling us what will happen, quantum mechanics tells us what might happen, and with what probability. Take the famous example of an electron. If you try to measure exactly where it is, you lose the ability to know exactly how fast it's moving. And if you measure its speed very precisely, you no longer know exactly where it is. This limit is called the Heisenberg uncertainty principle, and it tells us that there are pairs of things we simply can't know at the same time with perfect accuracy. So when physicists talk about where a particle is, they don't point to one spot. They give a range, a cloud of possibilities. The same goes for other properties, like spin, charge orientation, and even whether a particle has decayed. We don't know until we measure it, and even then, what we get is random, though the randomness itself follows rules. Are the laws of physics really laws if they only give probabilities? It's like asking whether the rules of dice rolling are laws. You know the dice will land on one of 6 numbers, and you can calculate the odds. But you can't say which number will come up in any single throw. Each roll is random, but the randomness itself is structured. After many rolls, the patterns become clear. Quantum mechanics is like that, but on a much deeper level. It's not just that we don't know which outcome will happen. It's that the outcome doesn't exist until it happens. One way to picture this is with the famous thought experiment known as Schrödinger's cat. Imagine a cat in a sealed box with a device that has a 50% chance of releasing poison based on the decay of a radioactive atom. According to quantum mechanics, the atom is both decayed and not decayed until someone opens the box. That means the cat is also both alive and dead, not just unknown, but in a true mix of states. Only when we open the box and look does the system choose an outcome. This is a metaphor to show how quantum systems exist in a superposition of all possibilities until they're measured. What decides the outcome? This is still one of the great mysteries of physics. Some interpretations suggest that the act of observation causes the collapse of possibilities into a single result. Others propose that all possible outcomes happen, but in separate parallel realities. A branching multiverse where every possibility is real, just not in our universe. No matter which interpretation you choose, the core idea remains. Quantum laws don't control exact events, they shape probabilities. They tell us the odds, not the outcome. So what does this mean for our understanding of laws? Are they weaker because they don't predict specific events? Not necessarily. In fact, the statistical rules of quantum mechanics are among the most accurate laws we've ever discovered. The predictions they make match experimental results to many decimal places. In the world of particles, that's the gold standard. Quantum laws may not tell you what will happen, but they tell you everything about how likely each outcome is. They don't remove structure from the universe, they define a new kind of structure. This blending of randomness and precision is one of the most striking features of the quantum world. Imagine flipping a coin that lands on heads or tails, but where the coin itself is described by a precise equation. The outcome is random, but the process is ruled by math. That's how particles behave. Their motion, interactions, and even their very existence are all described by something called a wave function, a kind of mathematical shape that spreads across space and time, showing where the particle might be and what it might do. When the particle is measured, the wave function collapses into a single result. But before that, it holds all possible futures. It's a way of saying that reality isn't fixed at the bottom. It's fluid, shaped by rules that leave room for chance. This also means that even the smallest events in the universe can't always be traced to a clear cause. At the quantum level, some things really do just happen. A particle might appear in one place or another with no reason beyond the underlying probability. That randomness then gets amplified when many particles interact, which could affect the larger world. This might sound unsettling, a universe built on chance rather than certainty. But it's also what makes things like creativity, life, and consciousness possible. If the universe were perfectly predictable, there would be no room for surprise, no space for freedom. The unpredictability of quantum events might be the hidden engine behind everything from mutation in DNA to the activity in human brains. In labs around the world, scientists have split photons, entangled particles, and created setups where the order of events seems to depend on what we choose to observe. They've shown again and again that the quantum world doesn't behave like a clockwork machine. And yet, out of that weirdness, the world we know still emerges. Laws, even probabilistic ones, still shape reality. There's something humbling about this. The laws of physics are not always about control or certainty. They don't dictate every detail, but they frame the possible. They draw the boundaries of what can happen, and within those boundaries, they let nature decide. Decoherence and the birth of classical laws. To understand decoherence, we have to start with superposition, the idea that a quantum particle isn't in one state, but in a mixture of many states at once. An electron, for example, doesn't travel along one path. It moves through a superposition of all possible paths. A photon doesn't go through one slit in an experiment. It goes through both until it hits a detector. These superpositions are fragile. They work only in very controlled conditions, in near-perfect isolation, with no outside interference. But in the real world, nothing is ever perfectly isolated. Everything is always interacting with something else, with air molecules, with light, with heat, with gravity. And as soon as a quantum system starts to interact with its environment, the superposition begins to break down. This is decoherence. It's not that the quantum system chooses a state. It's not that it gets measured in the traditional sense. Instead, it gets entangled with its surroundings in a way that makes the original superposition impossible to recover. The particle's possible states become mixed with the states of trillions of other particles, the air, the walls, the ground. The delicate balance of quantum interference disappears. What's left is something that looks classical. Decoherence turns the clean quantum patterns into messy, unreadable noise, and that noise gets spread out across the environment so widely that it can never be undone. The superposition is still there in theory, but it's become so tangled with everything else that it's lost forever. This process happens incredibly fast. A single particle in a vacuum might stay in superposition for seconds or even longer, but a particle in the open air decoheres in a fraction of a second. A human-scale object made of trillions of atoms and constantly interacting with its surroundings decoheres almost instantly. That's why we don't see superpositions in daily life. We don't see fuzzy cats or tables that are in two places. Decoherence keeps everything looking definite. This idea helps explain how classical laws emerge from quantum ones. Imagine a ball rolling down a hill. From a classical point of view, its path is clear. Gravity pulls it downward, friction slows it down, and its motion follows a smooth, curved line. But every atom in the ball is still a quantum object. In theory, each one could be in a superposition. So why don't we see the whole ball behaving that way? Because decoherence ties the atoms together. The ball is constantly interacting with itself and with the environment. That interaction keeps it locked into a single classical state, or at least a state that behaves like one. The result is what looks like a solid, predictable object obeying Newton's laws, but underneath it's still a swarm of probabilities. This also sheds light on why measurement matters so much in quantum physics. A measurement isn't just someone looking at a particle. It's any interaction that entangles the system with something large and messy, with a measuring device, or a detector, or even just the air. Once decoherence happens, the particles' superposition can no longer be observed. The outcome becomes definite. It may not be determined, but it becomes real in the way we experience reality. This means the classical world is not separate from the quantum world. It's not a different kind of physics. It's just what quantum physics looks like when systems become large, messy, and entangled. It's what happens when the rules of superposition meet the overwhelming complexity of everything else. In that collision, patterns collapse, randomness disappears, and solid laws emerge. But decoherence also reveals something fragile about our world. The clarity we see, the regular motion of planets, the ticking of clocks, the behavior of objects, is a kind of illusion. It's real in practice, but built on something that's fundamentally uncertain. The laws of classical physics are not the foundation. They are a high-level description of something deeper. This is why some physicists say that the laws we see, the ones we teach in school and rely on every day, are emergent. They aren't written into the core of reality. They arise from the way billions and trillions of quantum events average out over time. Decoherence doesn't create new rules. It just makes the quantum rules fade into the background. What's left is the world we see. This understanding also hints at where the boundary lies, if there even is one. How small does something have to be before decoherence stops and quantum weirdness returns? We know that atoms can be in superposition. We know that molecules can. Experiments have even shown interference patterns in large molecules made of hundreds of atoms. The bigger we go, the harder it gets. But the line is blurry. There is no sharp cutoff where quantum stops and classical begins. It's a gradual shift, governed by how much a system interacts with the world around it. Some scientists are now exploring this boundary directly. They're building quantum systems that stay isolated longer. They're creating environments where decoherence is delayed. They're trying to hold superpositions together for longer and longer times. These efforts are crucial for building quantum computers, machines that rely on quantum states to store and process information. In such systems, decoherence is the enemy. Every stray photon, every vibration, every unintended interaction can collapse the state and ruin the calculation. So researchers work to isolate their systems as much as possible, shielding them from heat, light, and noise. These technologies are forcing us to confront the deep structure of reality. As we push back against decoherence, we begin to see the rules behind the curtain. We see that what we call laws depend on scale, on environment, on interaction. The deeper we go, the more the simple laws of the everyday world begin to blur. What is a universe with no laws? What if there were no laws at all, not even strange or unknown ones, but truly none? No rules to guide how particles behave, no patterns in space or time, no constants, no structure, no cause and effect. Could anything exist in such a universe? Consider a single hydrogen atom, just one proton with one electron. In our universe, that atom is stable because of the electromagnetic force. The electron is attracted to the proton, and it settles into a specific energy level. This happens because there are consistent equations. equations we've tested and confirmed. If those equations didn't exist, the atom wouldn't hold together. Now go a step further. Take 2 hydrogen atoms and 1 oxygen atom. In our universe, those can join to make a molecule of water, but that requires stable forces, fixed rules, and a reliable structure to space and energy. If even one part of that system changed randomly, if charges flipped or the strength of the bonds changed unpredictably, the molecule would fall apart. Without laws, there would be no atoms, no molecules, no chemistry. And without chemistry, there's no chance for life, planets, or stars. There's not even a chance for stable energy. Light wouldn't follow a path. Space itself might not stay the same from one instant to the next. Time might fracture into moments that never connect. Even chaos needs a foundation. In our universe, randomness exists. In quantum mechanics, in radioactive decay, in thermal motion, but it's always within a framework. There are rules about when and how randomness happens. It's not lawless, just uncertain. That difference is key. Remove the framework entirely, and you don't just lose predictability. You lose the ability to define anything at all. Some physicists and philosophers have asked whether we could even define a universe with no laws. Would it even be a universe in any meaningful sense, or just a set of disconnected events, or no events at all? In many ways, the idea becomes impossible to pin down, because the very words we use, event, space, change, pattern, all depend on some kind of law beneath them. In a world without rules, there are no frames of reference. It's not just uninhabitable, it's unknowable, unthinkable, even unformable. Without laws, maybe there isn't a universe at all. People have simulated imaginary universes with different physical constants, different forces, different starting conditions. In most cases, the results are lifeless. Only a very small set of parameters leads to long-lasting complex structures, and even fewer seem able to support life. This is one reason why people talk about fine-tuning. Our universe doesn't just have laws, it has just the right laws. Still, it's worth asking, is it logically possible to have a world with no consistency, where randomness is total and structure never forms? Some thinkers suggest that even this idea collapses on itself. Total randomness, they say, is not a kind of order, but it still has a property, the absence of pattern, and that property is itself a kind of rule. If something is completely random, then that's a consistent feature, which means total lawlessness might be impossible, or at least internally contradictory. Maybe some kind of framework always exists, even if it's not one we can grasp. Others suggest that our own minds are tuned only to understand systems that can be understood. If we ask what it would be like to live in a universe with no rules, we may be asking a meaningless question, like asking what it's like to be a square circle. Everything we think and know is possible only because we live in a universe that allows thought and knowledge. The laws of nature govern possibility itself. The mathematical universe hypothesis. The mathematical universe hypothesis says that math isn't just a tool we use to understand the world, it is the world. Reality itself, in all its forms, atoms, galaxies, people, thoughts, is made of mathematical structures. It's one of those ideas that at first feels a little abstract, maybe even like a word trick. But once you start looking closely at how math appears in nature, it becomes harder to ignore. Because everywhere we look, from the orbits of planets to the spirals in seashells, from the growth of plants to the behavior of electrons, we find math. We find patterns, equations, ratios, symmetries, constants. Even chaos has rules. Why should that be? Why should math, something invented by humans with chalk and paper, do such a good job describing the universe? Why do particles behave according to formulas? Why do the laws of motion, electromagnetism, and quantum mechanics work across billions of light years? One answer is that math works because the universe is ordered, and math is just our best language for talking about that order. But the mathematical universe hypothesis takes a bolder step. It says math works so well not because it describes reality, but because it is reality. This idea was most famously explored by Max Tegmark, a physicist at MIT. He asked a very simple question. If there is a way to describe the universe using mathematics, then why not say that the mathematical description is the universe? That we're not mapping reality with equations. We're revealing what it truly is underneath. In this view, the universe is like a giant living equation. All the particles, all the forces, all the energy and space, they're not sitting on top of math. They are math. Think of a circle. A circle can be described by a formula. X squared plus y squared is equal to r squared. That's a clean, simple equation. Now imagine a three-dimensional shape, like a sphere. It also has a formula. A cube has one too. So does a sine wave, so does a spiral galaxy. These shapes can be built using numbers and logic. Now imagine something more complex. A tree, a weather system, a nervous system. Even these can be described mathematically if you go deep enough. Fractals can look like ferns and clouds. Neural networks can be modeled with graphs and functions. Suddenly, the line between math and nature starts to blur. And here's the key idea of the mathematical universe. If something can be described completely using mathematics, then that mathematical structure is that thing. There's no need to imagine anything behind the math. The numbers are the thing. The structure is all there is. This solves a few deep puzzles. For one, it explains why the universe is so orderly. If it's made of math, then of course it follows rules. Math is nothing but rules. Equations don't change depending on who's looking at them. 2 plus 2 is always 4. The Pythagorean theorem always holds. It also explains why the same math works everywhere, why the same laws apply whether you're on Earth or halfway across the galaxy, because the entire universe is one single huge mathematical object, and every part of it follows from the same basic structure. And if the universe is a mathematical structure, then maybe every mathematical structure exists, not just this one. That means there could be other universes, with different numbers, different constants, different dimensions, all made of different math. Not just alternate realities, but fully formed mathematical realities with their own laws and logic. In Tegmark's view, this is called the Level 4 multiverse. It's not made of atoms and energy, but of math itself. Every possible mathematical structure exists somewhere, as a real universe. But of course, this idea raises big questions. For one, what does it mean to exist mathematically? If a shape or an equation exists on paper or in a computer, is that the same as existing physically? Is there a difference between imagining a structure and being inside one? And what about consciousness? If the universe is math, does that mean we, our minds, our thoughts, our feelings, are also just parts of a mathematical pattern? It's not an easy idea to accept. Our experience feels real, solid, physical, but that's just how the pattern feels from the inside. According to this idea, what we call physical is just a special case of mathematical. Think of a video game. The characters inside the game follow certain rules: how they move, what they see, how they interact. From their point of view, those rules are the laws of their world. But outside the game, we know those rules are just code, math running on a processor. Could our reality be something similar? A kind of naturally existing mathematical world where everything, even time and space, is part of the structure. Of course, there are skeptics. Many physicists argue that this view goes too far. They say math is a tool, a powerful, beautiful tool. But it doesn't exist in the same way the universe does. They argue that just because we can describe something with math doesn't mean the math is the thing. They also point out that many mathematical structures are inconsistent or incomplete. Not all math leads to real, stable systems. And just because something exists in a mathematical sense doesn't mean it can hold stars, planets, or life. Still, the more we study nature, the more mathematical it seems. The shapes of crystals, the orbits of planets, the probabilities of quantum particles. Even the behavior of black holes can be described almost entirely by equations. In fact, some scientists say the best theories are the ones that are most beautiful, the ones with the simplest, cleanest math. As if the universe itself prefers elegant solutions. Maybe this isn't something we can ever test. Maybe it's more of a philosophical stance than a scientific theory. But it changes the way we ask questions. If the universe is math, then the laws of nature exist not because they were chosen or designed, but because they had to. They are the result of the structure itself, the unfolding of a logical pattern that has no outside, no beginning, and no reason beyond itself. The simulation hypothesis. Are the laws just programming? As our own technology has advanced, especially in computer graphics and simulations, we've started to see how detailed and lifelike artificial worlds can become. Games today model water, fire, weather, and even human behavior using mathematical systems. The rules are invented, but once they're in place, they give rise to environments that feel real, even to the people playing them. In many of these virtual worlds, the environment behaves according to internal rules, a kind of physics. But these rules aren't ultimate truths. They're written by game developers or designers. They can be tweaked, broken, or patched. A character might be able to walk through a wall after an update. A spell might be removed or changed, and none of this is strange within the context of a simulation. The code is what defines reality inside the system. So if our universe is a simulation, then maybe the same thing is happening on a larger scale. Maybe our physical constants, the speed of light, the strength of gravity, and the charge of the electron aren't eternal truths. Maybe they're values plugged into a cosmic program, variables in an unimaginable system running on something we can't see. In this view, the universe didn't begin with a bang because of natural causes. It booted up. This might sound fantastical, but it has been taken seriously by some thinkers. Philosopher Nick Bostrom laid out a formal argument in 2003 that shook many people. He said that if any advanced civilization in the universe ever reaches the point where it can run very large and detailed simulations, and chooses to do so, then simulated beings could easily outnumber real ones. If that's the case, then it's more likely that we are one of the simulations than one of the originals. It's a probability argument, not a proof, but it challenges how we think about our place in reality. And if the simulation hypothesis is true, then everything we believe about natural laws changes. Because the rules wouldn't be laws of nature in the usual sense. They wouldn't be discovered. They'd be assigned. Like lines in a software file. Like gravity equals 9.8 meters per second squared. Or the fine structure constant equals 1/137th. Those numbers, which we now treat as fundamental, could simply be chosen for effect. Just good enough to allow a stable, complex world to form. Just right for life to arise and keep running. In fact, this could even explain some of the strange coincidences in physics. The way so many constants seem finely tuned for life. Maybe they're tuned because someone wanted a world that could support observers. This also opens up the idea that the universe might not be as smooth as it looks. In a simulation, things only need to be detailed where someone is looking. In video games, the mountains in the distance don't really exist in full. They're just visual effects. If you walk toward them, the game engine fills in more detail. But behind the scenes, much of the world is empty until needed. Could something like that happen in our universe? Some physicists have looked for signs. They've wondered if there's a limit to the resolution of space, a smallest possible distance like pixels, or whether the randomness in quantum mechanics might be driven by a hidden process, like a random number generator, or whether the speed of light acts like a kind of frame rate, limiting how fast anything can happen, like a cap on processing. The more we learn about the universe, the more it sometimes looks like a machine, a very elegant, very deep machine, but a machine nonetheless. Now, if the universe is a simulation, who built it? Some imagine aliens, a post-human civilization from the far future, running ancestor simulations to learn about their own history. Some imagine a purpose. Maybe we're part of a science experiment, or a test, or even a game. Others say the question doesn't matter, because even if we're simulated, this reality is the only one we know. The rules are still the rules, even if they're artificial. If this world is a simulation, then what's the real world like? The world in which the simulation is running? We might never know. Just like characters in a game can't see the players, we might be trapped inside a reality that hides its own source. We might only ever see the rules we're given, never the system that made them. But that brings us back to the nature of laws. Because if the simulation hypothesis is true, then the laws of physics are like software. They exist to make the simulation consistent, functional, and interesting. They aren't necessary or eternal, and they could be rewritten. That's a very different picture from the one most scientists work with. It turns the laws of nature from deep truths into engineering solutions, and it makes our search for meaning a bit more complicated. Are we studying the universe, or just the settings in a program? Still, even in this framework, the rules still matter. They still guide the behavior of matter, energy, and time. Whether written by nature or by some distant intelligence, they are what define our world. The meta-law problem. Why do laws behave lawfully? When we talk about the laws of nature, we usually take one big thing for granted, that these laws don't just exist, but that they behave in consistent, logical ways. They don't flicker in and out, they don't change randomly, they don't rewrite themselves each morning, they hold with unbelievable reliability. But why should that be true? If laws behave lawfully, then what ensures that? What makes the laws themselves follow rules? In other words, are there laws of laws? What some call meta-laws. This might sound like splitting hairs, but it gets to the heart of one of the most puzzling features of the universe. Not just that there are laws, but that they seem to be deeply ordered, stable, and structured. There's no reason, at least not one we can see from inside the system, why this should be the case. After all, we could live in a universe where gravity only works on weekdays, or where the charge of an electron slowly increases over time, or where the strength of the strong force fluctuates depending on the location in space. But our universe isn't like that. The laws don't drift. So what holds the laws themselves in place? One possibility is that the laws are just brute facts. They simply are what they are. They don't need a deeper explanation. They aren't caused. They just are. But many thinkers have found that answer unsatisfying. Because if we're trying to understand why the universe is the way it is, then stopping at "it just is" feels like giving up. If everything else, particles, galaxies, biology, consciousness, can be studied and explained in terms of causes and patterns, why should the most important part of all, the structure of the laws themselves, be the one thing we don't ask questions about? So others suggest that there might be a deeper layer. Maybe the laws we see are not truly fundamental. Maybe they arise from some deeper, more abstract framework. This is where the idea of meta-laws comes in. A meta-law would be a rule that governs how other laws work. For example, it might say that all physical laws must be time-symmetric, or must follow mathematical consistency, or must be expressible in a certain kind of language. It would be like a rule book that sets the boundaries for what kinds of laws can exist in a universe. But that immediately raises a further question. What enforces the meta-law? We've just kicked the mystery up a level. If laws need rules to follow, and those rules are meta-laws, then what keeps the meta-laws consistent? Suddenly, we're staring into what seems like an endless staircase. Laws upon meta-laws upon meta-meta-laws. Each one explaining the one below it, but each one needing its own explanation in turn. It starts to look like an infinite chain, or maybe a loop. This is the meta-law problem. If we want to build a complete understanding of the universe, we can't just stop at what the laws are. We have to ask why they are the way they are. But every time we find a deeper answer, we discover that it, too, needs explaining. Some philosophers think this infinite chain might be unavoidable. Just as some ancient thinkers believed that the Earth rests on a giant turtle and then asked what the turtle rests on, and so on. We might be stuck asking why forever. There's no final answer, just layer after layer. Others think there might be a stopping point, a kind of ultimate rule or principle that doesn't need to be explained. Something so basic, so self-evident, that it holds up the entire structure of reality without needing support itself. But no one knows what that would be. Maybe the laws emerge from a process, like patterns forming in sand dunes from the wind, or order emerging in a snowflake as water freezes. In this case, the laws might not need a meta-law to guide them. They might just be what naturally happens when enough simple elements interact. In modern physics, there are ideas like this. Some researchers think that space, time, and even causality might emerge from something deeper, something that isn't spatial or temporal or causal. Quantum entanglement, for instance, might be more fundamental than space itself. So maybe the laws we see are just the visible tips of a deeper, dynamic process that doesn't need fixed rules. Still, even in that view, we're left wondering, what determines the rules of emergence? What shapes the way order arises from chaos? We've just changed the wording. Instead of asking what the laws are, we're now asking what kind of process can make laws. In our universe, the same rules apply in the early universe, in the present, and presumably into the far future. They are astonishingly clean. This doesn't look like something thrown together at random. It looks to many like a deep structure, one that demands an explanation. Even mathematical physicists struggle with this. When they build theories, they rely on certain tools: symmetry, consistency, logic. But why should the universe care about mathematical beauty? Why should physical laws obey group theory, or differential equations, or geometric relationships? Is there a meta-law that says all valid universes must be mathematically coherent? And if so, why? Religious and spiritual thinkers sometimes see the order of the laws as a sign of design, that behind the system is a mind or an intention. In this view, the meta-law might be the result of choice or will. But that raises its own set of questions about the nature of the creator, the origin of intention, and the reason for choosing these laws instead of others. In a way, it's just another way of saying that the laws need a source, and that source must be lawful too. So we're left with a kind of paradox. On one hand, the laws of nature are astonishingly stable. They seem almost mathematical in their precision. But on the other hand, their very stability creates a deeper mystery. It's a question that takes us beyond science and into philosophy. To answer it fully, we would need to step outside the system, to see not just the laws, but the framework behind them, and maybe even the rules behind that framework. From simplicity to complexity, are laws designed for computation? Some researchers have pointed out that the universe seems to behave like a giant computer. Not in a metaphorical sense, but literally. Every particle interaction is like a logic gate, a process where inputs become outputs according to fixed rules. Every quantum transition, every collision, every wave of light, every orbit, all of it is a form of computation. Information goes in, gets transformed, and comes out. Over time, this constant processing builds more and more complexity. If this is true, then it makes sense to ask whether the laws of physics are somehow tuned for this kind of behavior. Are they the kinds of laws that make it easy for a universe to compute things? Are they the sort of rules that allow information to be stored, copied, transmitted, and evolved over time? One clue comes from a strange feature of physics. The laws seem to strike a balance between rigidity and flexibility. If the laws were too simple, say a universe with only gravity and no matter, nothing interesting would happen. On the other hand, if the laws were too wild, changing randomly all the time, nothing stable could form. But our universe sits in the sweet spot. The laws are fixed and clear, but not boring. They allow patterns to form and grow. They allow systems to evolve, adapt, and remember. They allow local events to build into global structure. That's what computation needs. That's what life needs. The idea that physical laws might be optimized for computation is closely related to the concept of computational universality. This is the idea that a system, even a very simple one, can simulate anything else as long as it follows the right rules. Alan Turing proved this in the 1930s with his model of a universal computer. Later, people like Stephen Wolfram showed that even tiny programs, simple grids of black and white squares, can create surprisingly complex patterns over time. This has led some to suggest that the universe might be one such system, a kind of universal computer whose laws are just simple instructions that, when run at large scale, produce complexity. In this view, the laws aren't just compatible with computation, they're ideal for it. They make it easy for structures to store information. They make it possible for systems to remember previous states. They make room for feedback, loops, and growth. Even the way particles and forces work seems to support this. Particles like electrons and quarks have fixed properties. They act like bits of information. They don't blur or change unless acted on. Fields and forces let that information interact. And quantum mechanics, with its strange mix of certainty and probability, lets particles explore many possible paths at once, like a system running multiple calculations in parallel. The result is a kind of engine. The laws of physics move things forward. They process inputs into outputs. They let the universe do things. And in doing so, they allow the universe to build, layer upon layer, more and more complexity. From this point of view, the big question isn't just why does the universe follow laws, but why do those laws work so well for computation? One possible answer is that it's a selection effect. If the laws didn't allow complexity, life could never have emerged. There's also something else. The laws we see seem to be not just computable, but efficiently computable. Calculations in the real world don't seem to take forever. Processes in nature, like chemical reactions, or orbits, or neural signals, all unfold at speeds that match up. Nature seems to have built-in speed limits and timeframes, like Planck time, but within those, things run smoothly. Computation happens, but it doesn't bog down. Could this be a hint that the universe's rules were optimized not just for computation, but for fast, practical computation? In this light, the universe starts to look less like a machine and more like a program, designed or selected for just enough order and just enough freedom to support structure, growth, and change. So whether or not the laws were truly chosen, and whether or not there's a programmer or a multiverse or just blind chance behind it all, the fact remains, our universe behaves like a system designed for computation, and that might be the key to understanding why the laws are what they are. Do laws arise from information theory? Information theory is a field that began in the mid-20th century, mostly with Claude Shannon's work on how to send messages clearly through noisy channels. At first, it had nothing to do with the universe. It was about radio signals, telephone lines, and how many bits you could fit into a second of transmission. But over time, people began to notice that the rules that guide how information moves, changes, and gets stored seem to mirror many parts of physics. Take entropy, for example. In thermodynamics, entropy is a measure of how spread out or uncertain things are. In information theory, entropy is a measure of how much information is needed to describe something. The connection is mathematical. The two definitions of entropy are nearly the same, just written in different languages. That's already strange. Why should the way heat moves in a gas match the way bits move through a channel? Now zoom out to the entire universe. Some researchers believe the reason we see laws at all is because information needs rules. You can't store or move information in a system that's completely random, but you can work with it in a system like ours. One of the boldest ideas in this area is that physical laws themselves might emerge from information theory. Imagine, for instance, that information is the one thing that truly exists. The bits themselves, patterns of yes and no, of on and off, are the base. Then, the universe we see is what happens when those bits arrange themselves in the most efficient, logical, or consistent ways. Some call this idea algorithmic reality. That means the world works because of algorithms, step-by-step procedures that turn inputs into outputs. You can think of these like the laws of physics, but not fixed laws handed down from above. Instead, they're patterns that form when information systems settle into stable behaviors. Here's one way to imagine it. Think of Conway's Game of Life, a famous computer simulation. It's made up of a grid of squares. Each square can be on or off, alive or dead. There are only a few simple rules for how each square changes based on its neighbors. But when you run the simulation, complex patterns form. Shapes appear, grow, split, and interact. Some even look like they're alive. The laws of this little world come entirely from the starting rules, and those rules are just a few lines of code. Now scale that up. What if our universe is the large-scale version of something like this? What if the laws of motion, the rules of quantum mechanics, and the structure of atoms are just the natural results of simple rules applied to huge amounts of information? This might also explain why our laws are so mathematical. The patterns we see are there because those are the only patterns that make stable systems of information. Systems that can run without falling apart. Systems that can compute. Some people take this idea even further and suggest that the universe might be built from something like algorithmic compression. That means the simplest possible program that still creates the complex universe we see. If that sounds abstract, here's a way to think about it. If you have a long repeating string of numbers, you can often write it more simply. For example, 10, 10, 10, 10, 10, 10 can be described as 6 repeats of 10. That shorter version contains all the same information, but in a more compact form. Nature may do the same thing. Maybe the laws we see are the most compressed way to create a universe like ours. This would explain why the universe seems to prefer simplicity under the surface. The basic equations are short. The constants are few. The rules are tight. But from that simple base, complexity explodes. The simple rules happen to be the best ones for running a wide range of behavior. Another example comes from black holes. When you try to store information in a black hole, you might expect that the more matter you add, the more information it can hold. But it turns out that the limit isn't set by the volume inside the black hole. It's set by the surface area of its event horizon. This is deeply weird. It suggests that the information in a region of space doesn't depend on how much space there is, but only on the boundary. This is known as the holographic principle, and it hints that space itself may not be what it seems. Maybe the three-dimensional world we live in is really a projection of information stored on a two-dimensional surface. That idea, which came from string theory and quantum gravity, fits perfectly with the idea that information is fundamental. In fact, some researchers now think the entire universe might be a hologram, created from information encoded on some distant boundary. If true, then everything we see, touch, and measure, even time itself, could be a kind of output from an underlying algorithm. We may also be able to test some of these ideas. Physicists are now asking questions like, if reality is built from information, are there pixels of space and time? Are there lowest limits to how small distance or time can be? Could there be signs of digital rounding errors in the fabric of the cosmos? And what would that mean for the laws we live by? If they come from information theory, then they aren't fixed commands. They're the natural results of how data behaves. There's something poetic in this idea that beneath all the matter and fields, there is only pattern, only rules for how bits can combine and change. It makes the universe feel less like a machine and more like a story written in code, where each frame leads to the next, where each scene follows a set of internal rules. It would also mean that everything is part of one great process, a computation, running forward in time, following laws etched into logic itself. The Higgs field and the mass-giving mechanism. In the early moments after the Big Bang, the universe was filled with energy and light, but it didn't yet have many of the properties we now take for granted. One of the most important missing features was mass. The particles that would later form atoms and galaxies were massless. They moved at the speed of light and could not slow down. Without mass, they could not clump together or form anything stable. The universe at that time was full of potential, but not yet structure. So where did mass come from? The answer, as far as we know, begins with a strange kind of invisible field that fills all of space, the Higgs field. It's like an invisible ocean that everything must move through. According to the current understanding of physics, the Higgs field is what gives mass to the fundamental particles of the universe. To picture how this works, imagine a field spread across space like fog across a valley. Every particle that moves through this field interacts with it in a slightly different way. Some particles are barely affected. They move almost freely, like a bird gliding through mist. Others push against the fog and find their motion slowed, as if dragging through thick syrup. The more a particle interacts with the Higgs field, the more resistance it feels, and this resistance is what we experience as mass. It's not quite the same as weight. Weight depends on gravity and where you are. Mass is more basic. It's the thing that tells how much energy is needed to move a particle or stop it. It's what makes an object have momentum or cause a push when it collides with something else. Without mass, particles would never form atoms, and atoms would never build anything. The Higgs field itself came into being as the universe cooled after the Big Bang. Before that, it didn't have any effect. It was like a smooth surface at the top of a hill, symmetrical, balanced, and inactive. But as temperatures dropped, the symmetry broke. The field fell into a new state, like a ball rolling down the hill and settling into a valley. This new state had a non-zero value everywhere. In simple terms, the field turned on, and space itself began offering resistance to particles. This spontaneous symmetry breaking is the same kind of process that allows other forces to separate and become distinct. When the Higgs field settled into its new state, it reshaped the way particles behave, and it did so permanently. From that moment on, mass was possible. The actual particle connected to this field, the Higgs boson, was discovered in 2012 by the Large Hadron Collider. It's not what gives mass directly, but it's the evidence that the field exists. The discovery was a major breakthrough because it confirmed that this invisible background, the Higgs field, is real. It's something physical, something woven into the fabric of space. What's especially fascinating is how this fits into the bigger question of why the laws of nature allow mass at all. If the Higgs field had behaved differently, if it had stayed zero or settled into a different kind of pattern, particles would not have gained mass. They would have remained light-speed travelers forever. Everything would still be energy racing across an empty sky. But the laws we observe don't just allow mass. They set up a universe where mass emerges naturally. The shape of the Higgs field's potential energy, the way it curves and dips, seems to guide the field into that non-zero state. It's as if space is designed to give particles the ability to rest and to build. Why that curve? Why that shape? That part we don't yet understand. It's one thing to say how the Higgs field works. It's another to ask why the rules are written in a way that makes it work this way at all. There's nothing obvious that requires the Higgs field to behave the way it does. The shape of its potential energy is something we measure, but not something we can yet explain. In principle, the field could have taken on many forms. It could have been unstable. It could have decayed. It could have had a different value. If it had been just slightly different, electrons might not form stable atoms. Protons could decay too fast. The universe could be radically different. And so the Higgs field joins the list of physical ingredients that seem to sit in just the right range to make complex structures possible. Some physicists believe that the value of the Higgs field might be determined by the same kinds of ideas explored in theories like the multiverse. In different parts of the larger cosmic landscape, the Higgs field might have different values. Others think there may be a deeper, undiscovered law that explains why the Higgs field behaves as it does. Some grand unifying theory could show that the shape of the field's energy potential is not random, but required. Maybe symmetry, once again, is playing a hidden role, guiding the form of the laws themselves, even if that symmetry must be broken to bring the world into being. There are still puzzles within the Higgs story. One of them is why the Higgs boson is so light. According to quantum theory, it should get huge corrections from other particles, pushing its mass much higher than what we observe. This is called the hierarchy problem, and it suggests that something is missing in our understanding. Maybe new particles are balancing it out. Maybe the Higgs is part of a larger system, like in supersymmetry or string theory, or maybe the mass is just what it is, and we live in a universe where it happens to be small. The fact that mass exists at all points to a deeper level of physical law. One where the quiet, ever-present field that fills all of space is the stage on which everything plays out. The laws of nature not only allow such a field, they seem to depend on it. We can see the effects clearly. The mass of an electron, a proton, or even a Higgs boson itself is something we can measure. But the reason these masses appear as they do, why the Higgs field chooses this value, still sits beyond our reach. Dark energy and the law that shouldn't exist. For a long time, scientists thought they had a clear picture of how the universe works on large scales. Gravity pulls things together, galaxies collide. Over time, everything slows down. It made sense that the expansion of the universe, the way space itself stretches, would gradually decelerate. That's what gravity does. It pulls back against expansion. But in the late 1990s, two independent teams of astronomers were studying very distant supernovae, exploding stars so bright they can be seen across billions of light years. These events serve as cosmic mile markers, helping researchers measure the distance to faraway galaxies. When the data came in, something was clearly wrong. The distant galaxies weren't just moving away from us, they were accelerating. The universe wasn't slowing down, it was speeding up. This discovery shocked the physics world. According to general relativity, the structure of space and time is shaped by energy and mass. But nothing in known physics explained a force that could push space itself apart faster and faster. There was only one way to account for it. Something unknown had to be acting across all of space, adding pressure where none was expected. This strange force became known as dark energy. The name doesn't explain much. Dark just means we can't see it. Energy suggests it has something to do with the structure of space, but those are only guesses. We still don't know what dark energy is. It's not a particle. It doesn't form stars or galaxies, but it dominates the universe. It makes up nearly 70% of the total energy content of everything. Yet it hides in plain sight. The simplest idea is that dark energy is a constant, something built into space itself. This isn't a new idea. In fact, Einstein once proposed a similar concept called the cosmological constant. At the time, he thought the universe was static, neither expanding nor contracting. But when Hubble discovered that space was expanding, Einstein called his constant a mistake. Now it seems that idea may have been ahead of its time. The cosmological constant means that even empty space has energy. Not just space filled with particles or radiation, but the vacuum itself. If that's true, then space naturally stretches. The more it stretches, the more space there is, and the more energy there is to stretch it further. It's a feedback loop. The universe keeps expanding, and the dark energy doesn't dilute. It keeps driving the process. Quantum physics says the vacuum should have energy, a lot of it. Particles constantly flicker in and out of existence, even in the emptiest void. When physicists try to calculate how much energy the vacuum should have, the number they get is enormous. So enormous, in fact, that if it were true, the universe would have torn itself apart instantly after the Big Bang. The number predicted is about 10 to the power of 120 times bigger than what we actually see. This isn't a small error. It's the biggest known mismatch between theory and observation in all of science. It's like predicting the weight of an object should be more than the mass of the entire universe, and then measuring it to be lighter than a feather. No one knows why this number is so small. Some think the vacuum energy is real, but something cancels most of it out. Others think our understanding of the vacuum is flawed. Still others believe dark energy isn't a constant at all, but a new kind of field, slowly changing over time. That idea is called quintessence. It's a stretch, but so is everything else. Normal matter pulls things together. Dark energy pushes them apart. It behaves as if empty space has a kind of negative pressure, one that makes it want to expand. And the more space there is, the stronger that effect becomes. This doesn't fit into any neat law. Most of physics is about how things respond to forces, but dark energy doesn't come from interaction. It doesn't seem to respond to particles or change its behavior based on its environment. It's just acting everywhere, always in the same way. Why does the universe even have this feature? Why does the vacuum carry energy at all? And why that particular value? There's nothing in our current understanding of physics that demands this. Gravity didn't require it. Quantum mechanics didn't predict it. The standard model of particles doesn't explain it. It had to be discovered by accident, and even then, it still doesn't make sense. In a way, dark energy is a kind of law that shouldn't exist. It doesn't follow from any deeper rule. It just seems to be a fact of the universe. One possibility is that dark energy is a sign that something is deeply wrong with our understanding of space, time, and energy. Maybe general relativity is incomplete. Maybe quantum field theory breaks down at large scales. Maybe we need a new framework entirely, one that links the geometry of space to the contents of space in a completely new way. There are ideas like modified gravity or emergent spacetime, but none are confirmed. Dark energy shows us that the laws we thought were complete might only be the surface layer. Beneath them, there may be structures we don't yet understand. Not just different forces or particles, but new kinds of rules. Rules that don't look like laws at all. Dark energy controls the future of the universe. If it stays constant, the universe will keep expanding forever, growing colder and more empty as stars fade and galaxies drift apart. If it increases, the universe might rip itself apart in a final burst of acceleration. If it decreases, expansion might slow down and reverse, ending in a collapse. In each case, the fate of everything comes down to this one hidden feature: loop quantum gravity and the breakdown of classical law. One of the biggest problems in physics is that we have two powerful theories, each incredibly accurate in its own domain, that refuse to work together. So scientists have spent decades searching for a deeper theory, something that can unify general relativity with quantum mechanics. One of the most promising candidates is something called loop quantum gravity, or LQG for short. The idea behind loop quantum gravity is that space isn't smooth. Maybe it's made of tiny pieces, little loops of energy or geometry, like the fabric of reality is woven together from microscopic threads. In normal physics, space is treated like a smooth, continuous stage where things happen. But in LQG, space is more like a mesh or network. You can't divide it forever into smaller and smaller parts. There's a smallest possible length called the Planck length, which is about 100 billion times smaller than a proton. Below that, space itself loses its meaning. If space is made of loops, then geometry itself becomes quantized. Volume, area, even angles and curves, all come in discrete chunks. You can't have just any amount of space, just like you can't have half a photon. The universe becomes pixelated at its most fundamental level. And this changes how we think about the laws of nature. Because if space and time are made of loops, then the classical laws can't hold up when you zoom in far enough. They're only approximations that work when space looks smooth. Down at the loop level, those rules begin to fade. It's like watching a painting up close. From a distance, it looks like a clean image, but up close, you can see it's made of tiny brushstrokes. The same may be true of the laws of physics. What seems smooth and continuous is actually rough and stitched together. One of the most exciting places to test this is in black holes. According to classical general relativity, the center of a black hole, the singularity, is a point of infinite density, where gravity becomes so strong that space and time collapse. But infinities are usually a sign that our math is breaking down. Loop quantum gravity offers an alternative. Instead of a singularity, the loops of space resist being crushed. Gravity doesn't go to infinity. Instead, the collapse reaches a minimum size and then potentially reverses. This could mean that inside every black hole is not a dead end, but a doorway, maybe even the beginning of a new region of space. In classical cosmology, the universe also begins from a singularity, a point of infinite heat and density. But if space is made of loops, then perhaps the universe didn't begin from a true singularity. Maybe the universe before the Big Bang collapsed down to a minimum size and then bounced outward, creating what we now see. In both cases, black holes and the early universe, the classical laws fail. LQG offers a way to break through that wall by showing us what happens beyond the limits of smooth space. And in doing so, it rewrites the laws themselves. Even time gets affected. In LQG, time might not be fundamental and instead might emerge from the relationships between the loops, from how the geometry changes. Some researchers think that at the deepest level, time disappears. There's only change, not a flow of moments, but transformations between quantum states. What we experience as time might be more like a convenient illusion. If time and space are not fundamental, then the laws that rely on them become effective tools, not absolute truths. They work well at large scales, but they're not the real rules of the universe. They're shadows of deeper processes that loop quantum gravity is trying to uncover. This idea that the classical laws are not final opens up new paths. It means we should be cautious about assuming that what we see today will always hold true at all scales. Just as Newton's laws were replaced by Einstein's when we looked closer, and just as Einstein's laws begin to crack under quantum conditions, perhaps LQG will be one more step in the direction of truth, or at least toward a better approximation of it. But loop quantum gravity is still a work in progress. It's hard to test directly because the scales it deals with are so tiny and the energy so high. We don't yet have the tools to see the loops directly or to probe the Planck scale. But scientists are working on it, looking for indirect signs, patterns in the cosmic microwave background, traces in black hole behavior, hints in gravitational waves. It's slow, difficult work, but the potential payoff is enormous. If loop quantum gravity is right, it could help us not only unify physics, but also rewrite our deepest ideas about space, time, and the laws of nature themselves. Causal sets, replacing space-time with logical structure. Imagine peeling away the smooth fabric of space and time, stripping the universe down to its most basic pattern. Flashes of things happening, one after another, each one causing the next. This is the idea behind causal sets. A bold vision that suggests space and time are an illusion born from logic and order. The heart of causal set theory is the idea that the universe is fundamentally discrete, not made of atoms or particles, but of events. And those events are linked by causality. That's it. Everything else, from space to time to the shape of the universe, comes later. The causal links form a growing web, like a family tree of moments, and from that web, we get all the structure we observe. Normally, we imagine space-time as a fabric that bends and warps, but in causal set theory, that fabric is just an approximation, like how a movie seems to move smoothly, even though it's made of individual frames. The causal set is like those frames, but in a far deeper sense. Why propose this? One reason is that our current physics struggles to describe what happens at extremely small scales. Causal set theory says, maybe the problem is we're still assuming there is a space-time fabric to begin with. Maybe we've mistaken the shadow for the real thing. If instead, we start with a growing network of discrete events, and only later ask what kind of geometry those events seem to form, we might get a universe that naturally avoids the breakdowns caused by trying to force quantum rules into a smooth geometric stage. The logic of causal sets is surprisingly simple. Each event in the universe is represented by a point. If event A can influence event B, meaning that light or any signal could travel from A to B, then there's a link from A to B. These links obey a strict order. If A leads to B and B leads to C, then A leads to C. And if two events can't influence each other, if they're space-like separated in relativity, then there's no link between them. This creates a partial ordering, a kind of before and after, that doesn't require space or time as we normally think of them. As the universe evolves, new events get added to the causal set, but they aren't placed into space. They're placed into a logical structure, a kind of cosmic ledger, recording what came before and what comes after. It's this sequence of influences that forms the true backbone of reality. And because each event only depends on those before it, the entire structure grows in a way that reflects causality itself. It offers a solution to why the universe is so well behaved. If space-time is emergent, then that order isn't imposed from outside. The laws are reflections of how the structure grows. You don't need a separate framework to enforce them. It also helps avoid the infinite compression that comes with smooth space-time. If you can divide space endlessly, then at some point you get into trouble. You reach singularities where the math says densities become infinite, but if the universe is made of discrete events, there's a minimum spacing between them. So where do the laws come from in this picture? They come from the way the causal set grows. The rules that decide how new events attach to the old ones, what they can be influenced by and what they can influence in turn, act like physical laws. Different rules of attachment create different kinds of geometry. Some causal sets grow into something that looks like flat space. Others resemble curved space or even expanding universes. In this way, the geometry of the universe is not a fixed thing, but the result of choices made by the network itself. That means time is granular, not continuous, but made of steps. There is no master clock outside the system. Time is internal. It's the rate at which new events become real. This raises questions about determinism. If events get added one by one, does that mean the universe is writing itself as it goes, with no fixed outcome? Or is the pattern of growth determined by some higher logic, a kind of cosmic algorithm? Different models of causal set theory suggest different answers. Some allow randomness. Others lean toward deterministic patterns. But either way, it puts agency back into the fabric of the universe. Not the agency of a person, but the agency of a growing logical structure. Superdeterminism, the death of free will and randomness. When entangled particles are measured, their results are strangely correlated, as if they know what the other one is doing, even across vast distances. Most physicists explain this by saying there's no hidden communication between particles. Instead, the results are simply unpredictable, and yet still follow certain statistical patterns. The idea is that nature doesn't care what we expect. Outcomes are just probabilistic. But what if it isn't? Superdeterminism offers an alternative. Maybe the outcomes of quantum experiments aren't random. Maybe they only seem that way because we don't see the full picture. According to this idea, everything that happens is determined by hidden variables, values baked into the universe from the beginning. That includes not just the particles being measured, but also the experimenters themselves, their devices, their settings, and even their decisions. If the entire universe follows a strict chain of cause and effect, then nothing is truly free. That includes your choice to look at a particle's spin or polarization. In a superdeterministic world, your decision to measure a certain way was predetermined, just like the particle's response. The strange correlations between entangled particles wouldn't be spooky or mysterious. They'd just reflect a shared history, an invisible connection going back to the beginning of time. This challenges one of the most basic ideas in science, that we can set up fair experiments. In quantum tests, we often assume that the settings of a measuring device are independent from the system being tested. This assumption is called measurement independence, and it's key to interpreting results. But superdeterminism says that assumption might be false. The choice of settings and the system's state might be deeply connected, because both come from the same starting point. If that's true, the randomness we see in quantum mechanics would be just an illusion, an artifact of not knowing the underlying variables. Free will, too, would be an illusion. Every action, every thought, every decision would be the result of long chains of cause and effect, going all the way back to the origin of the universe. This is deeply uncomfortable. It goes against how we experience the world. We feel like we choose what to do. We feel like outcomes can be uncertain. We build entire systems, legal, moral, social, on the idea of responsibility and freedom. Superdeterminism pushes back against all of that. It says that the flow of time doesn't leave room for true choice. But there are reasons physicists are taking it seriously. Quantum theory has always had a weird status. It's been incredibly successful at predicting experimental results, but it doesn't explain why things work the way they do. And for some thinkers, that's not enough. They want a deeper explanation, something that brings back clarity, even if it costs us freedom. Superdeterminism is one way to do that. It allows us to imagine a universe where everything is caused and nothing is mysterious. Entanglement becomes a matter of shared initial conditions. Quantum unpredictability becomes a reflection of ignorance, not true indeterminacy. The universe becomes a perfect machine, humming along according to hidden blueprints. Critics argue that if everything is predetermined, including the way we choose experiments, how can we ever tell if it's true? Any result we get could be explained as just part of the script. This creates a risk. The theory might be impossible to prove or disprove, and in science, that's a problem. But not everyone agrees that it's untestable. Some physicists are looking for clever ways to check for hidden correlations, tiny signs that our experimental settings might not be as independent as we think. Others are trying to build concrete models, mathematical systems that show how superdeterminism could work in practice. It's early work, and progress is slow, but the questions being asked are serious. Superdeterminism forces us to ask what we mean by law. If laws of nature dictate everything, even our thoughts and measurements, then we are part of those laws, not outside them. We're not observers standing apart from the world, shining a light on its secrets. We're expressions of the same deep structure that we're trying to understand. It also reshapes the concept of information. In standard quantum theory, the act of measurement reveals information that wasn't there before. It's created in the act of observation. But in a superdeterministic world, all information already exists, just hidden. Measuring doesn't create anything new. It just uncovers part of a vast, fixed tapestry. When you read a book, you experience the story as it unfolds moment by moment. But the entire plot, the beginning, the twists, the ending, is already written. You can't change it, even though you feel surprised. Superdeterminism suggests that reality might be like that. Others reject this view strongly. They argue that science should preserve the idea of independence, of true randomness, of real agency. They say that even if superdeterminism is logically possible, it's too extreme, too hollow. It strips away meaning. Superdeterminism raises more questions than it solves. But that's often where the most important progress begins. By questioning our assumptions, we might uncover deeper truths, even if those truths are uncomfortable, even if they rewrite what it means to be human. The role of topology in shaping physical law. In most everyday experiences, shape is a surface detail, but in the deeper structure of the universe, shape can be something much more profound. It may be that the shape of space itself helps determine the kinds of physical laws that exist. This is the realm of topology, a branch of mathematics that studies how things are connected, twisted, or knotted, without concern for their size or exact form. And when it comes to the very fabric of reality, topology might be one of the most important ingredients of all. Imagine a two-dimensional creature living on the surface of a balloon. that creature would experience a curved, closed universe, one where going in a straight line long enough would eventually bring it back to where it started. But now imagine a different kind of surface, like a donut or torus. A creature on that surface could also walk in straight lines and return, but the patterns of return would be different. The possible motion, the way waves might spread, the behavior of fields, all of it could depend on this deeper topology. And that's just for simple 2D surfaces. Now imagine how strange things can get in 3 or more dimensions. This is where modern physics starts to take topology seriously. For example, in theories of quantum gravity, the way those bits connect could define a kind of underlying topological skeleton. The rules that emerge from that structure might look like our familiar physical laws, but they're shaped from the connectivity beneath. The same kind of idea plays out in theories of extra dimensions. String theory, for example, doesn't just propose more dimensions. It proposes that those extra dimensions are compactified, curled up into specific shapes at every point in space. These shapes, called Calabi-Yau manifolds, are complex topological objects, and different shapes allow different kinds of particle behavior. Change the shape, and you change the spectrum of particles. It's a way the geometry of the hidden universe dictates what kinds of forces and matter can even exist. But topology can also show up in more accessible physics. For instance, in certain materials known as topological insulators, the behavior of electrons isn't just about energy or motion. It's about how the wave functions of the electrons wrap around the structure of the material. The electrons are forced to behave in specific ways because of topological constraints. This is real, measurable, and experimentally verified. It hints at a broader principle, that some laws might arise not because of energy or symmetry, but because of shape. There's even speculation that the vacuum of space might be threaded with topological defects. These are like knots in the field lines of space itself. They could be relics from the early universe, left over from symmetry-breaking events as the cosmos cooled. In some models, these defects create stable structures like cosmic strings or monopoles. If real, they would be examples of how the deep shape of space imprints features into the laws of physics. In physics, we often describe the evolution of systems as moving from one state to another, but topology can limit which transitions are possible. Some shapes can't smoothly deform into others without tearing. That's a powerful constraint. It suggests that the universe might be stuck or channeled into certain behaviors just because of how it's stitched together. There are hints from cosmology that the topology of the entire universe could leave a mark on the patterns we observe in the cosmic microwave background. If the universe is finite but wraps around in a non-trivial way, we might see repeated patterns in the sky. So far, the data doesn't show strong signs of this, but the possibility remains. The shape of the whole cosmos might be hiding in plain sight. In quantum field theory, topology plays a role in even more abstract ways. There are objects called instantons, configurations of fields that are stable because of topological features. They contribute to certain rare processes, like tunneling events or changes in vacuum state. Again, these aren't just curiosities. They're part of how the rules of quantum behavior actually unfold. Topology helps us ask questions we didn't even know how to phrase before. What if time has a different topology than space? Could it be circular or branching or composed of loops? Some models of quantum gravity suggest time might emerge from a deeper structure that has no time at all, just networks of causality arranged topologically. In that case, even causation itself might be a product of how the universe is wired together, not a fundamental rule. Topology doesn't care about distance, energy, or motion. It cares about relationship, about what's connected to what and how. That's a different way of seeing the universe, not as a set of things with properties, but as a pattern of relationships with consequences. If that's true, then the laws we observe might just be the echo of this hidden structure. They might be the vibrations of something deeper, whose influence we feel in every law we write down. And if the topology of space is not fixed, If it can change, evolve, or fluctuate, then the laws themselves might shift too. That would mean we live in a universe where not even the rules are safe from change, where what we call law is just the current state of a vast, hidden architecture. Are black holes cracks in the law? Black holes challenge multiple layers of physics. They mix gravity and quantum mechanics in a way we don't yet know how to handle. If you try to describe what happens to a particle that falls into a black hole, quantum theory tells you that the particle's information, its properties, should never be lost. But general relativity tells you that once something crosses the event horizon, that information disappears forever. This conflict has led to one of the most famous puzzles in physics, the black hole information paradox. Some physicists think this paradox is a sign that there is a deeper theory behind both general relativity and quantum mechanics, one that combines them and removes the contradictions. Others think it could mean the laws themselves are incomplete, and that new kinds of behavior might emerge at the edges of black holes, where the rules get fuzzy. In either case, the message is clear. We don't understand everything, and black holes might be the best place to learn more. Even the structure of black holes seems strange. There's the event horizon, a boundary that you can cross going in, but never come back from. From the outside, it looks like a point of no return. But from the inside, time and space switch roles. Going inward becomes as unavoidable as moving forward in time. How can we talk about cause and effect, or laws that govern outcomes, when time itself loses its meaning? Then there's Hawking radiation. According to Stephen Hawking's famous prediction, black holes aren't entirely black. They slowly leak energy over time, caused by quantum effects near the event horizon. If black holes evaporate, where does the information go? Does it just vanish? That can't be allowed in quantum theory. But if it doesn't vanish, where does it end up? Hawking radiation appears to carry no information about the inside of the black hole, and yet that would mean the laws of physics don't hold in full. Some proposed solutions are radical. One idea is that the information is somehow encoded in subtle changes in the Hawking radiation, an idea called unitarity preservation. Another is that information is stored on the event horizon in some unknown way. No one has directly observed Hawking radiation. No one has been close to a black hole. And no one has tested physics at the scale where gravity and quantum mechanics both matter in full. In that sense, black holes are like locked doors. We can feel that something strange is going on behind them, but we don't yet have the tools to open them. In the 1970s, physicist Jacob Bekenstein suggested that the more mass a black hole has, the more entropy it contains. Black holes have huge entropy compared to normal objects. What is all that information about? If we don't know what the microscopic ingredients of a black hole are, how can we even talk about its entropy? This is where some theorists think that black holes are not just objects that obey the laws, they might reveal them. Some believe that studying how black holes bend, twist, and ripple space-time might offer glimpses into the deeper layers of reality where the laws take shape. Are physical laws the same in other dimensions? When we talk about the laws of nature, we're usually thinking about how things work in our universe, a place with 3 dimensions of space and 1 of time. But what happens if you imagine a universe that doesn't have the same number of dimensions as ours? Could the laws we know still work? Let's start by imagining a universe with fewer dimensions than ours. What would it be like to live in just 2 spatial dimensions instead of 3? A 2-dimensional universe would be like living on a perfectly flat sheet of paper. There would be no such thing as up or down, only forward, backward, and side to side. You could still move around and interact with things, but your world would be very limited. For example, in such a universe, complex organisms like us might not even be possible. Internal organs would be tricky to arrange without overlapping, and blood flow would have trouble getting around obstacles without leaking. Even the basic laws of physics would behave differently. In our world, gravity pulls objects together in 3 dimensions. But in a 2-dimensional space, the way gravity works would change. The strength of the force between objects would drop off more slowly with distance, or might not behave the same way at all. The same is true for electric and magnetic fields. They depend on how space is shaped and how energy can spread through it. Shrinking space to fewer dimensions changes those rules. Sound waves need a medium to move through, and they spread out in 3 dimensions. In a 2-dimensional world, the way sound spreads would be totally different. It might echo in weird ways or travel farther than we expect. And light, if it existed at all, might not spread in circles like it does here. It might not even be able to form the kind of electromagnetic waves we rely on to see. But things get even more bizarre when you imagine a universe with more than 3 spatial dimensions. What if there were 4, 5, or even 10 directions to move in? Physicists have tried to explore this idea using mathematical models. One surprising result is that gravity, as we know it, doesn't behave well in higher dimensions. In our universe, gravity gets weaker as things move farther apart. Specifically, it follows what's called an inverse square law. If you double the distance between 2 objects, the gravitational pull between them becomes 4 times weaker. That rule only works in 3 dimensions. In a universe with more than 3 dimensions, the strength of gravity would drop off even faster. That leads to a big problem. Stable orbits would be impossible. Planets couldn't orbit stars. Moons couldn't circle planets. Everything would either spiral inward and crash or fly off into space. Stars might not be able to form at all, and even atoms, which depend on balanced forces, could break apart. That means a higher dimensional universe wouldn't just be a weirder version of ours. It could be completely different. If matter did exist, it might look nothing like the matter we know. The familiar structures of galaxies, solar systems, and life might not appear. Some researchers believe that 3 dimensions of space is the only number that allows for the kind of complexity and stability that life and chemistry need. Light would face similar problems. In our universe, light travels in waves through space. Those waves spread out in all directions, getting weaker the farther they go. But in a 5-dimensional space, light would spread even faster, becoming too thin to carry energy over long distances. That could make vision impossible. There'd be no way for eyes to collect enough light to form images. Even communication might break down, since light would vanish too quickly. Shapes like cubes and spheres, which are easy to imagine in 3 dimensions, have strange and unfamiliar versions in higher dimensions. A 4-dimensional cube is called a tesseract. It can't be drawn directly in our space, but it follows rules that mathematicians understand. If space had 5 or 6 dimensions, these strange shapes would be the norm. And time? That's even harder to figure out. In our universe, time is one-dimensional. It moves in a single line from past to future. But what if time had more than one dimension? That would mean events could unfold in more than one direction. Cause and effect might not be fixed. You could have multiple timelines that interact or fork off in different ways. Some theories in physics, like certain versions of string theory, suggest that more dimensions of space, and maybe even time, could exist in some hidden form. In fact, string theory itself requires more than 3 dimensions of space to make its equations work. These extra dimensions are thought to be tiny and hidden from view, but they might still affect how particles behave and how forces interact. If that's true, then the laws we observe in our universe might actually be shaped by these unseen dimensions. So maybe the reason our universe has the laws it does, and not some other set, is because of how many dimensions it has. Change the number of dimensions, and you change the rules. Some laws vanish, some change completely, and others simply stop making sense. There's even a possibility that in a different dimensional universe, there could be new forces or fields. Maybe, instead of gravity pulling objects together, there's a kind of push that holds things apart. Maybe particles aren't points, but threads or surfaces, and they move in ways we can't describe in our space. We can't step into a 5-dimensional world and run experiments, but we can explore them using math, computer models, and clues from high-energy physics. If we ever find solid evidence that other dimensions exist, it would be one of the biggest discoveries in science. It would mean that the universe is far more complex than we ever imagined. Maybe our universe is balanced on a knife's edge, with just the right number of dimensions to allow light to travel, atoms to form, and life to grow. Maybe if the universe had been shaped even slightly differently, it wouldn't have laws at all, or at least none that we could recognize. Could we one day rewrite the laws of nature? Right now, we don't have control over the laws of nature. We discover them. We describe them with equations. We use them to build technologies, from rockets to quantum computers. But all of it is based on working within the laws. No one has ever changed the gravitational constant. No one has slowed the speed of light. No one has made a proton decay faster or frozen the expansion of the universe. These are baked-in features of reality, or at least they seem to be. Some theories in physics, like cosmic inflation or the multiverse hypothesis, suggest that new universes are constantly being created, tiny bubbles that form and grow, each with its own laws and constants. These universes might be forever out of reach, or maybe with enough knowledge and energy, they could be made intentionally. A far future civilization might discover how to trigger a universe to form, a pocket of space-time that buds off from our own, sealed and self-contained. If that's possible, perhaps they could design a universe, set the laws themselves, choose the values of gravity, the strength of the forces, even the number of dimensions. In this view, the laws of nature are not fixed truths, but parameters in a system, and once you understand the system well enough, you can program it however you want. But what about rewriting the laws inside this universe? This idea is more speculative, but there are cracks in the door. One area of interest is the vacuum of space. Empty space is full of energy from quantum fields that are always fluctuating. Some physicists believe that by manipulating these fields, we might be able to change the structure of space-time. In extreme theories, it might be possible to reprogram certain properties of matter or energy by affecting the vacuum state they emerge from. If you think of the universe as a kind of computation, then modifying the underlying state might allow you to change the behavior of everything built on top. Some speculative models of advanced technology suggest that gravity might not be an unchangeable force, but something that can be bent, shaped, or even turned off in special zones. We already bend space with mass. That's how gravity works. But we've only ever observed it passively. If we learned how to manipulate mass energy in the right way, or how to interact with hypothetical particles like gravitons, we might be able to change how gravity behaves locally. Another idea involves changing the effective constants of nature. Perhaps these values could shift under special conditions, for example, inside extremely high-energy environments, or near exotic objects like cosmic strings or domain walls. If a civilization could create or control such environments, they might be able to engineer zones of altered physics. In more radical ideas, such as those found in digital physics or certain interpretations of quantum mechanics, the universe is not just law-governed, it is law-run. And if you can find the source code, then in theory, you can change it. Of course, this level of control is far beyond anything we can do now. We don't know if it's even possible. Some thinkers believe that if any civilization in the universe could reach a high enough level of technological maturity, say a type Vi or Viz on the extended Kardashev scale, it would eventually begin to manipulate the laws of physics themselves. Not just building megastructures or harnessing galaxies, but changing the operating rules of reality to suit their needs. That might include creating time loops, opening shortcuts through space, or altering causality in small ways. Others go further. What if our own universe was created by such a civilization? Perhaps intelligent life eventually gives rise to new universes in which intelligent life can again emerge. Over cosmic timescales, this would act like evolution. The laws that support complexity and thought would become more common because civilizations keep making more of them. So could we one day rewrite the laws of nature? It depends on whether the laws are truly fundamental or just part of a deeper structure. Right now we work within the laws. We try to understand them, model them, and use them. But the history of science shows that what once seemed absolute often turns out to be a special case. If our descendants, or other civilizations, can peer beneath the laws we know, they may just find a toolkit for reality itself. And on that wild note, this video must come to an end. What other weird and wonderful ideas would you like for us to cover next? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.